Out there in the darkness of space, far from any star, there are worlds drifting completely alone, planets with no sun, no warmth, no familiar sky. These are the most isolated planets in the universe, wandering through the galaxy like cosmic castaways. Today, we're uncovering their mysterious origins, incredible distances, and the shocking truth about life in total isolation. What is a rogue planet? Picture a planet moving through space with no sunrise, no seasons, no central star to circle. It does not belong to a solar system. It does not orbit anything. It travels alone through interstellar space, pulled only by gravity it barely feels. This is not a rare glitch or an exotic exception. It is a recognized planetary class. A rogue planet is a planetary mass object that does not orbit a star. That definition is simple, but it took decades of debate, argument, and new detection methods before scientists accepted it as real. According to NASA and the International Astronomical Union, a rogue planet, also called a free-floating planet or interstellar planet, is a body with a mass below the threshold required for nuclear fusion, meaning it is not a star or brown dwarf, and it moves through space without being gravitationally bound to a star. That one sentence changed how scientists understand planets. For most of modern astronomy, planets were defined by what they orbit. No star meant no planet. Objects without stars were assumed to be failed stars, gas clouds, or detection errors. The idea that full-size planets could exist entirely on their own was considered unlikely, even unstable. That assumption turned out to be wrong. Rogue planets are not theoretical leftovers or rare accidents. They are a natural result of how planetary systems form and collapse. They are produced in enormous numbers. Some are larger than Jupiter. Some are similar in mass to Earth. Many are older than the Sun. And once they are ejected, there is no mechanism to bring them back. They become permanent wanderers. To understand why rogue planets exist, the first thing to remove is the idea that planetary systems are calm or orderly. They are not. Planetary systems are violent environments, especially during their early formation stages. When a star forms, it does not form alone. It emerges from a collapsing cloud of gas and dust, surrounded by a rotating disk. Inside that disk, hundreds of planetary embryos begin forming at the same time. These young planets do not grow in neat lanes. They pull on each other. They scatter. They collide. They steal material. They fall inward. They get flung outward. Gravity decides everything, and gravity has no concern for balance or stability. Most planetary systems begin with far more planets than they end with. Some are destroyed, some are absorbed by the star, some survive in tight orbits, and many are thrown out completely. This is not rare behavior, this is expected behavior. The most common cause of rogue planets is multi-body gravitational chaos. In young planetary systems, several large planets often form at roughly the same time. These planets are massive enough to disturb each other's orbits. When three or more large bodies interact gravitationally, the system becomes unstable. There is no clean solution, no smooth compromise. Instead, the system enters a chaotic phase where orbits stretch, tilt, cross, and break. One planet might be pushed inward toward the star. Another might be pushed outward into a distant orbit. And one planet, usually the lightest, or the one that gets the worst gravitational encounter, gains enough speed to escape the system entirely. Once a planet reaches escape velocity, it is gone. There is no slowing down, no return path. The star no longer holds it. The planet enters interstellar space on a straight-line trajectory that can last billions of years. Computer simulations show that this happens often. In systems with multiple gas giants, ejection is not an exception. It is a likely outcome. The larger and more crowded the system, the higher the chance that one or more planets will be expelled. Even systems similar to our own could have lost planets early on. Some models suggest the early solar system may have ejected one or more ice giants before settling into its current layout. Those planets would still be out there. Stellar flybys, when other stars interfere. Planetary systems do not form in isolation. Stars are born in clusters. Dozens, hundreds, sometimes thousands of stars form close together inside dense regions of gas. In these crowded nurseries, stars pass near each other far more often than most people realize. When a star passes close to another star, their gravity overlaps. That overlap does not need to be direct or dramatic to cause damage. A close flyby can stretch planetary orbits. It can destabilize outer planets. It can weaken the gravitational hold of the host star just enough for a planet to escape. This is especially common for planets that orbit far from their stars. A passing star does not need to steal the planet. It only needs to disturb the balance. Once disturbed, the planet may drift outward, gain speed, and eventually leave the system entirely. Observations of star-forming regions show that these flybys were common during the early history of the Milky Way. Many planetary systems were disrupted before they ever stabilized. That means rogue planets are not just the result of internal chaos. They are also casualties of crowded stellar neighborhoods. Star clusters do not last forever. Over time, gravitational interactions between stars cause clusters to expand and dissolve. As the cluster collapses or disperses, stars move into new orbits around the galaxy. During this process, planetary systems experience repeated gravitational disturbances. Some stars lose planets. Some planets are exchanged between stars. Some planets are stripped away completely. In dense clusters, this process is even more severe. Planets in wide orbits are especially vulnerable. Their weak attachment makes them easy targets for disruption. Once detached, they drift away and never reconnect with another star. These cluster dynamics are one of the reasons astronomers believe the galaxy contains such a large population of free-floating planets. Every cluster that formed in the past contributed to the total. For years, many rogue planet candidates were misclassified as brown dwarfs. Brown dwarfs occupy a mass range between planets and stars. They are heavy enough to fuse deuterium briefly, but not heavy enough to sustain hydrogen fusion like stars. The problem is that mass alone does not tell the full story. Some rogue planets are massive enough to resemble brown dwarfs in temperature and brightness. Others are much smaller and colder. Without a host star to reference, classification becomes difficult. What separates a rogue planet from a brown dwarf is not just mass, it is formation history. Brown dwarfs form like stars through direct collapse of gas clouds. Rogue planets form inside planetary disks and are later ejected. Modern surveys now combine mass estimates, motion tracking, and formation modeling to distinguish between the two. This distinction matters because it confirms that planets do not need stars to exist. They only need stars to be born. Rogue planets emit almost no light. They do not reflect starlight. They are cold, dark, and distant. This makes them nearly invisible. The primary method used to detect them is gravitational microlensing. When a rogue planet passes between Earth and a distant star, its gravity bends the light of the background star. This creates a brief brightening that lasts anywhere from minutes to days, depending on the planet's mass. The event does not repeat. There is no orbit to track, no second chance. If scientists miss it, the planet is lost forever. This method does not care whether the planet has a star. It only cares about mass. That is why microlensing opened the door to discovering rogue planets in large numbers. Infrared surveys also detect the warmest rogue planets, especially massive ones that retain heat from formation. But most rogue planets are too cold to detect directly. They are inferred statistically, and those statistics changed everything. Early estimates suggested rogue planets were rare. Those estimates were wrong. Microlensing surveys revealed a staggering result. For every star in the Milky Way, there may be one or more rogue planets. Some studies suggest there could be 2 or 3 rogue planets for every star. That means hundreds of billions of free-floating planets in our galaxy alone. These numbers shocked astronomers. It meant that planetary ejection was not a side effect. It was a dominant process. Planet formation produces excess planets. Gravity decides which ones stay. The rest are discarded into interstellar space. This also means that when we look at the night sky, most planets are not orbiting stars. They are invisible, drifting through the dark between stars, passing silently through regions we assume are empty. Earth-mass rogue planets exist. One of the most surprising discoveries was the detection of Earth-mass rogue planets. For a long time, scientists assumed only large planets could survive ejection. Smaller planets were thought to be destroyed or absorbed before escaping. Microlensing data contradicted that idea. Earth-sized planets are ejected too. This means rocky worlds with solid surfaces, internal heat, and possibly atmospheres can exist without stars. They are not rare. They are part of the population. Their internal heat comes from radioactive decay and residual formation energy. Some models suggest that thick atmospheres could trap enough heat to maintain subsurface liquid water for long periods. This is not speculation pulled from fiction. It is based on known physics. Rogue planets are cold, but cold does not mean inactive. Rogue planets reveal how violent planetary systems really are. They preserve evidence of early chaos that stable systems hide. They also provide a way to study planets without stellar interference. No radiation, no stellar winds, no flares. This makes them clean laboratories for understanding planetary interiors and atmospheres. They also force scientists to rethink planet definitions. A planet does not need a star to exist. It only needs mass, structure, and origin. And the galaxy is full of them. Rogue planets are not leftovers from the distant past. They are still being produced today. Any system with unstable orbits can eject planets at any time. Binary stars increase the likelihood. Multiple gas giants increase the likelihood. Dense stellar environments increase the likelihood. The Milky Way is constantly generating new rogue planets. Every million years adds more. They spread throughout the galaxy, crossing spiral arms, passing near stars, entering regions where new systems will eventually form. Some may even pass through our solar neighborhood without us ever knowing. Rogue planets break the simplest assumption people have about planets. That assumption is ownership. Planets are not owned by stars. They are created by stars, shaped by gravity, and then released when conditions demand it. The universe does not prioritize stability, it prioritizes motion. And rogue planets are motion made permanent. They do not orbit, they do not return. They move forward, carrying the imprint of the system that lost them, long after that system has forgotten they were ever there. The first confirmed rogue planets. Long before the first rogue planet was ever detected, astronomers already suspected they had to exist. This was not based on imagination or guesswork, but on a problem that kept showing up again and again in computer simulations. When scientists modeled how planetary systems formed, they kept getting the same uncomfortable result. Stable systems like ours were the exception, not the rule. Most simulations ended with planets colliding, falling into their stars, or being thrown completely out of the system. For years, those ejected planets were treated as theoretical debris, something that might happen in equations but was impossible to prove in real space. There was no telescope powerful enough to see a cold planet drifting alone through the dark, and without a star nearby, there was nothing obvious to point at. So the idea remained stuck in papers and models, quietly accepted by some researchers and dismissed by others as untestable. In the early 1990s, a small group of astronomers began talking seriously about a method that could expose objects that emitted no light at all. The method was gravitational microlensing, a direct prediction of Einstein's general theory of relativity. According to the theory, mass bends space, and bent space bends light. If an object passed in front of a distant star, its gravity would briefly focus the star's light, making the star appear brighter for a short time. The object itself would remain invisible, but its mass would give it away. At first, microlensing was discussed mostly in relation to dark matter and compact stars. Using it to detect planets without stars sounded ambitious, slow, and unreliable. The events would be rare. The alignment would be perfect only for a short time. There would be no repeat signal. Many astronomers believed it was too impractical to build a field around. That hesitation began to fade as surveys improved. By the mid to late 1990s, dedicated microlensing projects were monitoring millions of stars at once, especially toward the dense star fields of the Milky Way's central bulge. Instead of studying individual targets, these surveys watched entire regions of the sky continuously, waiting for brief flashes that could only be explained by gravity passing in front of background stars. The first microlensing events detected planets orbiting stars, which already proved the method worked. But hidden in the data were stranger signals, events that lasted only hours or even minutes, far too short to be caused by stars or even typical planets in orbit. These signals did not repeat. They had no visible host star. They appeared once and vanished forever. At first, researchers were cautious. Short events could be noise, instrumentation errors, or background effects. But as more data came in, the pattern became impossible to ignore. The durations of the events matched what would be expected from planetary mass objects moving freely through space. The masses were too small to be stars. There was no detectable star nearby that could plausibly be the host. The simplest explanation, and eventually the only explanation that fit all the evidence, was that these were planets with no stars at all. By the early 2000s, teams working on projects like OGLE and MOA began publishing results that openly discussed free-floating planetary mass objects. At first, the language was careful. Papers used phrases like unbound planetary candidates or isolated planetary mass lenses. There was resistance to using the word planet. The concern was classification. If planets no longer needed stars, then the definition itself had to change. But as detections increased, the debate shifted. This was no longer about whether rogue planets could exist. It was about how many there were. One of the turning points came when statistical analysis showed that these short microlensing events were not rare anomalies. They were common. In fact, they appeared so frequently that the implied population was enormous. When astronomers extrapolated the data across the Milky Way, the numbers were staggering. The galaxy was not just producing rogue planets occasionally, it was producing them in bulk. The models suggested that there could be as many or more free-floating planets as there are stars. This was not a fringe estimate. Multiple independent analyses pointed in the same direction. This realization forced a shift in perspective. Rogue planets were no longer treated as lost objects or failures of formation. They became a normal outcome of planetary system evolution. Systems formed too many planets, and gravity removed the excess. The galaxy was not neatly organized into stars with tidy planetary families. It was filled with planets that had been expelled, scattered into the space between stars, moving through regions no one had ever seriously considered as planetary territory. Why we can't see them, and why microlensing changed everything. The reason rogue planets escaped detection for so long is simple. They are almost perfectly dark. Without a nearby star, there is no reflected light. Without nuclear fusion, there is no internal energy source powerful enough to make them glow visibly. Most rogue planets are only a few tens of degrees above absolute zero. Even large gas giants cool rapidly once they are cut off from their stars. After a few 100 million years, they fade into the background of space, indistinguishable from the cold vacuum around them. Traditional planet hunting methods fail completely under these conditions. The transit method depends on a planet passing in front of a star. No star means no transit. The radial velocity method depends on a planet pulling on its star and causing a wobble. No star means no wobble. Direct imaging works only for young hot planets near bright stars, and even then, it is extremely difficult. Rogue planets offer none of these signals. They do not announce themselves, they do not repeat, they do not stay in place. Microlensing does not care about light, it does not care about temperature, it does not care whether an object is a planet, a star, or something else entirely. It only responds to mass. This is why it became the key that unlocked the rogue planet population. When a free-floating planet passes in front of a distant star, its gravity acts like a lens, bending and focusing the star's light toward Earth. The result is a brief, smooth brightening that follows a precise mathematical curve. The shape of that curve reveals the mass of the object that caused it. For a star, the brightening lasts weeks or months. For a planet, it may last hours or even minutes. The smaller the mass, the shorter the event. This is why early microlensing surveys missed many rogue planets. They were not watching fast enough. Once observation cadence improved, the signals became obvious. Short events that had once been dismissed as noise suddenly stood out as planetary fingerprints. There is no second chance with microlensing. Once the alignment passes, it is gone forever. Astronomers cannot follow up, cannot re-observe the same planet, cannot take spectra or images. All they get is a curve, a duration, and a mass estimate. That limitation initially made some scientists uncomfortable, but as the number of detections grew, confidence increased. The statistics were clear. These were not rare coincidences. They were members of a vast, unseen population. As the implications spread through the scientific community, the tone of discussion began to change. Papers started using the word planet without qualifiers. Conferences included entire sessions on free-floating worlds. Observational programs were redesigned to capture even shorter microlensing events, targeting Earth-mass rogue planets specifically. What had once been an obscure prediction became a major research focus. The media response followed quickly. Headlines began to appear describing planets with no suns, worlds drifting through space, invisible planets filling the galaxy. While the language was dramatic, the underlying message was accurate. The Milky Way was not just a collection of stars with planets attached. It was a planet-rich environment where most planets were never seen because they had no light to give away their presence. The galaxy is filled with invisible worlds was not an exaggeration. It was a direct reflection of what the data showed. Every improvement in microlensing sensitivity revealed more of them. Every new survey confirmed the same pattern. The galaxy was packed with planets that no telescope could ever photograph. Planets that existed only as brief bends in starlight. Planets that proved their existence by briefly warping the background of the universe and then disappearing again into the dark, continuing their silent paths through interstellar space without ever orbiting another star. And once that realization took hold, it permanently altered how astronomers thought about planets, systems, and the true structure of the Milky Way. CFBDSIR 2149-0403, the planet that shouldn't exist. When CFBDSIR 2149-0403 first appeared in astronomical data, it immediately caused discomfort. Not excitement, not celebration, but confusion. It showed up as a cold, faint object moving through space on its own, with no visible star anywhere near it, detected during a survey that was never designed to look for planets at all. The Canada-France Brown Dwarf Survey was built to find brown dwarfs, objects heavier than planets, but lighter than stars, bodies that glow faintly from leftover heat, but never ignite nuclear fusion. That is what researchers expected to find, and that expectation shaped how the object was first described. CFBDSIR 2149-0403 appeared in infrared data as an isolated low-temperature object with unusual spectral features. Its light signature suggested methane absorption, something commonly seen in very cold substellar bodies. At first glance, this placed it comfortably in brown dwarf territory. But the deeper researchers looked, the less comfortable that classification became. Its brightness was lower than expected. Its motion through space did not match what was typically seen in older brown dwarfs drifting through the galaxy. And most importantly, its estimated mass landed right on the fault line between planets and brown dwarfs, a region astronomers had been arguing over for decades. The object was located roughly 130 light-years away, relatively close by galactic standards, and it was not orbiting any star. No companion could be found, even after careful follow-up observations. This immediately raised a question that could not be ignored. If it was a brown dwarf, how did it form alone, without a stellar system around it? Brown dwarfs usually form like stars, inside dense clouds of gas, often in groups or binaries. Finding one completely isolated was unusual, but not impossible. Finding one with such a low mass, however, was a problem. As teams began analyzing its properties more carefully, the mass estimates became the central issue. Based on its luminosity and temperature, CFBDSIR 2149-0403 appeared to have a mass somewhere between 4 and 7 times that of Jupiter. That range matters. The commonly used dividing line between planets and brown dwarfs is the deuterium burning limit, around 13 Jupiter masses. Objects above that threshold can briefly fuse deuterium. Objects below it cannot. CFBDSIR 2149-0403 fell well below that line. This placed it firmly in planetary mass territory, at least by mass alone. But mass was not the only issue. Formation history mattered too, and that was harder to prove. Did it form like a star, directly collapsing from a gas cloud? Or did it form inside a planetary disk and later get ejected? Without a host star, there was no direct way to trace its origin. This uncertainty ignited debate almost immediately after the discovery was published. Some researchers argued that calling it a planet was misleading. In their view, a planet should form around a star by definition. Others pushed back, pointing out that formation history could not always be reconstructed, and that mass and physical properties were more practical criteria. The object did not behave like a brown dwarf. Its gravity, atmosphere, and thermal profile matched models of giant planets far more closely than stellar remnants. The debate spilled beyond specialist journals. Science news outlets picked up the story, and the phrasing quickly became more direct. Articles asked whether this was truly a planet or something else entirely. Headlines questioned whether astronomers were stretching definitions too far. Is this even a planet? Became a recurring theme. Not because the science was weak, but because the discovery exposed how fragile existing categories really were. Why CFBDSIR 2149-0403 changed the rules. One of the reasons CFBDSIR 2149-0403 drew so much attention was its temperature. Estimates placed it at around 400 degrees Celsius early on, later refined to closer to 430 Kelvin, making it one of the coldest free-floating planetary mass objects ever observed at the time. This temperature range was consistent with young giant planets rather than older brown dwarfs, which tend to cool differently over time. Its spectral features showed signs of water vapor and methane, markers commonly associated with gas giant atmospheres. Size estimates also aligned with planetary expectations. Despite its mass, its radius was comparable to Jupiter's, again matching planetary models. Brown dwarfs, especially older ones, tend to contract more significantly. CFBDSIR 2149-0403 did not show that level of contraction, suggesting a different thermal and structural history. Its motion through space added another piece to the puzzle. The object appeared to be part of a young moving group, a loose association of stars and substellar objects that formed around the same time and share similar velocities. If this connection was real, it implied an age of roughly 50 to 120 million years. That youth mattered. A young age meant retained heat from formation, which explained its brightness without requiring a higher mass. It also supported the idea that the object formed in a planetary disk and was later ejected, rather than forming alone like a star. This was the moment when the conversation shifted. The object was no longer just an odd brown dwarf candidate. It became one of the strongest cases for a true rogue planet with planetary mass, planetary size, and planetary atmospheric features existing completely on its own. The classification debate intensified because CFBDSIR 2149-0403 sat in a region where labels stopped being useful. If it was a planet, then planets did not need stars. If it was a brown dwarf, then brown dwarfs could be lighter and more planet-like than previously thought. Either option forced astronomers to redraw boundaries. Some researchers proposed using formation pathways as the primary criterion, but this immediately ran into practical limits. Formation history is rarely observable. It must be inferred, and in many cases, it cannot be confirmed. Others suggested sticking strictly to mass-based definitions, which placed CFBDSIR 2149-0403 clearly on the planetary side. This approach gained traction, especially as more similar objects were discovered. As additional free-floating planetary mass objects were found, CFBDSIR 2149-0403 became a reference point. It was no longer an outlier. It was an early example of a class that was turning out to be common. Each new detection strengthened the argument that planetary mass objects could exist independently, and that the universe did not respect the tidy categories humans preferred. The controversy surrounding its classification did not fade quietly. It reshaped conference discussions, influenced how surveys labeled their findings, and pushed organizations like the IAU to acknowledge that their definitions were incomplete. The question was no longer whether CFBDSIR 2149-0403 was a planet or a brown dwarf. The real issue was that the line between those categories was no longer stable. CFBDSIR 2149-0403 forced astronomers to confront a reality they could no longer avoid. Planetary systems eject planets often. Planetary mass objects populate interstellar space in large numbers, and the presence or absence of a star is not a reliable way to decide what a planet is. Ogle 2016, BLG 1928, the smallest rogue planet ever found. Ogle 2016, BLG 1928 entered astronomy quietly, without images, without follow-up observations, without a glowing discovery photo to circulate online. There was no picture of a planet, no orbit traced, no star to point at. What existed instead was a short disturbance in light that lasted less than an hour and then vanished forever. That brief signal was all astronomers would ever get, and yet it was enough to overturn long-held assumptions about what kinds of planets could survive being thrown into interstellar space. The detection came from the optical gravitational lensing experiment, known as OGLE, a long-running survey that monitors dense star fields toward the center of the Milky Way. OGLE does not hunt planets the way most people imagine. It does not look for shadows crossing stars or for stellar wobbles. It watches millions of distant stars at once, night after night, searching for tiny, temporary increases in brightness caused by gravitational microlensing. The survey's strength lies in numbers and patience. It observes continuously, knowing that rare events only become visible when enough data is collected over long periods of time. In 2016, during routine monitoring of the galactic bulge, one star briefly brightened in a way that did not match typical microlensing events. The increase was smooth and symmetrical, exactly what gravity predicts, but it happened too fast. The entire event lasted just 42 minutes. For comparison, microlensing events caused by stars last weeks or months. Even Jupiter-mass planets usually produce signals lasting several hours. A 42-minute event was almost unheard of. At first glance, such a short signal could easily have been dismissed. Instrument noise, atmospheric effects, or data glitches can all create brief anomalies. But OGLE's observing setup is designed to filter those out. The light curve was clean. The shape was precise. The timing matched relativistic predictions exactly. This was not noise. It was mass passing in front of a star. When researchers modeled the event, the result was immediately unsettling. The mass required to produce such a short microlensing signal was extremely small on astronomical scales. The best fit pointed to an object with a mass comparable to Earth. Not a gas giant, not a Neptune-like world, an Earth mass object. Even more striking was what was missing. There was no sign of a host star, no secondary brightening, no distortion that would suggest a larger object nearby. If a star had been present, even a faint one, the signal would have shown it. The data showed nothing. The lensing object was alone. That meant the only explanation consistent with the observations was an Earth mass rogue planet, drifting freely through the galaxy. This was not supposed to happen. Before this discovery, most models assumed that small rocky planets would not survive the chaos required to eject them from a planetary system. Ejection requires strong gravitational encounters, usually involving giant planets. In those scenarios, smaller planets were expected to collide, fall inward, or be torn apart long before they could gain enough speed to escape. The idea that an Earth mass planet could be cleanly ejected, remain intact, and travel alone through interstellar space challenged those assumptions directly. The 42-minute duration was the key. Gravitational microlensing timescales scale directly with mass. There is no flexibility there. A shorter event means a lower mass. Astronomers ran alternative models, tested different distances, adjusted velocities, and explored every plausible configuration. The result did not change. The lensing object had to be planetary in mass, and it had to be very small. Because microlensing events do not repeat, OGL 2016 BLG 1928 could not be observed again. There was no chance to confirm it with another method. No spectrum could be taken. No infrared glow could be searched for. The entire case rested on that single light curve. That might sound fragile, but microlensing is one of the most mathematically rigid detection methods in astronomy. When the curve fits, it fits completely. There is no room for interpretation once the parameters are locked in. As the analysis circulated among researchers, the reaction was immediate and intense. Not because the detection was uncertain, but because of what it implied. If one Earth mass rogue planet could be detected in a limited dataset, then there had to be many more. Microlensing surveys sample only a tiny fraction of the galaxy at any given time. Detecting even one such object suggested a large underlying population. This forced astronomers to revisit population models. Earlier estimates of rogue planets were already high, suggesting that free-floating planets might rival stars in number. Those estimates, however, were dominated by Jupiter mass objects. OGL 2016 BLG 1928 indicated that the population extended all the way down to Earth mass planets. That changed the scale of the problem completely. It was no longer enough to say that giant planets get ejected. This showed that rocky planets do too. The shock was not emotional or dramatic, it was structural. Models of planetary system evolution had to account for a new outcome. Systems could not only lose their largest members, they could lose their smallest, most compact planets as well. That meant the early stages of planetary formation were even more violent than previously thought, and that stability was harder to achieve. The detection also highlighted just how difficult these planets are to find. A 42-minute signal requires constant monitoring and rapid data processing. Miss it by an hour, and the planet is gone forever. Many similar events must have occurred unnoticed before surveys reached the necessary cadence. OGL's success was not luck. It was the result of watching continuously, without bias toward what kind of planet might appear. The announcement of OGL 2016 BLG 1928 did not come with sensational language from the researchers themselves. The paper was careful, restrained, and focused on the data. But outside the technical literature, the reaction was stronger. Media coverage emphasized the scale of the discovery. An Earth mass planet, alone, drifting through space, detected only because it briefly bent the light of a star thousands of light years away. The phrase, "smallest rogue planet ever found," appeared repeatedly. and for once it was accurate. What made the discovery especially disruptive was that it removed a comforting boundary. Before this, it was easy to imagine rogue planets as frozen gas giants, failed versions of familiar worlds, large enough to endure ejection. Earth-like planets felt different. They were supposed to be anchored. They were supposed to need stable systems to exist. Ogle 2016, BLG 1928, showed that this belief had no physical basis. If a planet has mass, gravity treats it the same way, regardless of composition. Rock does not get special protection. This realization carried immediate consequences for how astronomers think about planetary systems as a whole. If Earth-mass planets are frequently ejected, then many systems may lose their inner rocky worlds early on. The planets we observe today might be survivors, not typical examples. The solar system's relative calm could be unusual rather than representative. Ogle 2016, BLG 1928, also sharpened interest in future microlensing missions. If current ground-based surveys could catch a 42-minute event by chance, space-based observatories with continuous coverage could detect many more. This single detection became a proof of concept, showing that even the smallest rogue planets leave detectable traces if the instruments are sensitive enough. The discovery did not answer questions about the planet's surface, atmosphere, or history. None of that information is accessible through microlensing. What it provided instead was something more fundamental. It proved that Earth-mass planets can exist independently of stars, not as rare accidents, but as members of a broader population shaped by gravitational instability. There was also a deeper implication that unsettled many researchers. If Earth-mass rogue planets are common, then the galaxy contains vast numbers of rocky worlds moving through space without stars. They are not habitable in any conventional sense, but they are also not destroyed. They persist. They carry the mass and structure of terrestrial planets into environments no one previously considered planetary. Ogle 2016, BLG 1928, did not open a new category. It exposed a hidden extension of an existing one. Rogue planets were already known. What changed was the lower limit. The floor dropped from gas giants to Earth-like masses in a single 42-minute signal. That brevity became part of the discovery's identity. 42 minutes was all it took to demonstrate that the processes that eject planets do not discriminate by size. Anything that forms in a system is a potential candidate for expulsion. Stability is not guaranteed. Survival is conditional. The planet itself continues moving through the Milky Way, unseen, untracked, unaffected by the attention it briefly received. It will never be detected again. Its importance lies entirely in what its detection revealed about the galaxy. Not through speculation, not through theory alone, but through a single, precise bending of light that matched gravity's rules perfectly and left no alternative explanation behind. Rogue gas giants, the frozen behemoths. Among all rogue planets, gas giants dominate both in size and in detectability. When astronomers talk about free-floating worlds, they are most often referring to Jupiter mass or super-Jupiter objects moving through interstellar space without a star. These are not rare exceptions. They are the most common type of rogue planet ever detected, not because they are more numerous than smaller rogues, but because their mass and heat make them easier to find. Their existence is tightly linked to how planetary systems form, destabilize, and violently reorganize themselves in their earliest stages. Gas giants form early. In young planetary systems, massive planets grow fast by pulling in large amounts of gas from the surrounding disk. This happens while the star is still young and the disk is still thick. Because of their mass, gas giants quickly become the dominant gravitational players in their systems. They shape the orbits of everything around them, including other giant planets. When multiple gas giants form in the same system, the outcome is rarely stable for long. Their gravity pulls hard, and small changes compound quickly. One close encounter between two giant planets can stretch orbits, tilt them, or send one planet inward while flinging another outward. In many systems, this phase ends with at least one gas giant being completely ejected. When a Jupiter-mass planet is thrown out of its system, it does not lose its identity as a planet. Its mass remains the same. Its atmosphere remains intact. What changes is its energy source. Cut off from stellar radiation, the planet begins a slow cooling process that can last billions of years. Unlike rocky planets, gas giants begin their lives extremely hot. During formation, gravitational compression releases enormous amounts of energy. Even after the surrounding disk disappears, these planets retain a large internal heat reservoir. This heat does not vanish quickly. It leaks out slowly through thick layers of gas, long after the planet has been expelled into darkness. This internal heat is the reason rogue gas giants are sometimes detectable at all. Even without a star, they emit faint infrared radiation. The younger the planet, the brighter it is in infrared. A newly ejected gas giant can glow strongly enough to be detected across dozens or even hundreds of light years. As it ages, the glow fades, but it never disappears entirely. The cooling process follows well-understood physical laws. Larger planets cool more slowly. Super-Jupiters, with masses several times that of Jupiter, can retain measurable heat for far longer than smaller planets. This is why most directly imaged rogue planets belong to the gas giant class. They are large, warm enough to emit infrared light, and their spectra reveal thick atmospheres dominated by hydrogen and helium. Observations show methane, water vapor, and carbon compounds, often in quantities similar to gas giants that orbit stars. The difference is not in composition, but in environment. These planets exist in isolation, exposed only to the weak background radiation of the galaxy. Their temperatures vary widely. Some rogue gas giants are still hundreds of degrees hot, especially if they are young. Others have cooled to temperatures comparable to Antarctica or colder. In extreme cases, surface temperatures drop low enough for atmospheric gases to condense into clouds of exotic compounds. Methane, ammonia, and water can form cloud layers that move slowly through the planet's atmosphere, driven by internal heat rather than stellar energy. Despite the word frozen, these planets are not inert. Deep inside, pressure remains enormous. Hydrogen exists in exotic states, compressed into metallic forms. Convection continues, transporting heat from the interior outward. Magnetic fields may still operate, generated by the motion of conductive materials deep within the planet. These internal processes do not stop just because the planet has no star. The isolation of rogue gas giants makes them scientifically valuable. Without stellar radiation interfering, astronomers can study their atmospheres in a cleaner way. There is no glare from a nearby star to overwhelm the signal. The light detected comes entirely from the planet itself. This allows for more direct measurements of temperature, composition, and atmospheric structure. For this reason, rogue gas giants have become important targets for infrared telescopes. The faint glow they emit peaks in the infrared part of the spectrum. Visible light telescopes are almost useless for finding them. Infrared instruments, however, can pick up their thermal emission, especially when surveys scan wide areas of the sky repeatedly. Early infrared surveys revealed dozens of isolated planetary mass objects, many of which were initially classified as brown dwarfs. As measurements improved, some of these objects were reclassified as planetary mass rogues based on their mass, temperature, and spectral features. Super-Jupiter rogues are particularly important. With masses several times that of Jupiter, they sit just below the threshold where deuterium fusion begins. These planets blur the boundary between planets and brown dwarfs. They are heavy enough to generate strong gravitational signatures, retain heat for long periods, and glow more brightly than smaller rogues. Their detection rates are higher, not because they are more common, but because they stand out more clearly against the cold background of space. These massive rogue gas giants likely come from systems that were especially unstable. Forming a super-Jupiter, requires a massive disk and rapid gas accretion. Systems that can produce such planets often produce several of them. Multiple massive planets in the same system almost guarantee violent interactions. When such systems destabilize, the outcome is often extreme. One planet may fall inward and be destroyed. Another may remain bound in a distant orbit. And one or more may be ejected entirely, carrying enormous mass into interstellar space. Once ejected, these planets follow long straight paths through the galaxy. They are no longer tied to a single star's orbit. They move on trajectories set by the velocity they had at the moment of ejection. Over millions of years, they drift far from their birthplaces. After billions of years, they are scattered throughout the galactic disk, passing through regions where new stars are forming, crossing spiral arms, and occasionally passing close to other stellar systems without interacting with them. The idea that these massive planets could exist in such numbers was not always accepted. Early models underestimated how often gas giants would be ejected. They assumed planetary systems would settle into stable configurations relatively quickly. Observations have shown that this assumption was optimistic. Many systems remain unstable for tens or hundreds of millions of years. During that time, ejection remains possible. Each unstable system adds to the rogue population. The faint infrared glow of rogue gas giants is not uniform. It changes with age, mass, and composition. Younger planets shine more brightly. Heavier planets shine longer. The cooling curves of these planets are now an active area of research. By comparing observed temperatures with models, astronomers can estimate the ages of rogue planets and reconstruct parts of their history. This turns rogue gas giants into time markers, revealing when and how planetary systems lost their members. The James Webb Space Telescope plays a critical role here. JWST operates primarily in the infrared, exactly where rogue gas giants emit most of their energy. Its sensitivity allows it to detect much fainter objects than previous telescopes. JWST can observe isolated planets that are colder, older, and farther away than any previously studied. This extends the observable population deeper into the galaxy and closer to the true average rogue planet, not just the youngest or brightest examples. JWST's instruments also allow for detailed atmospheric analysis. By breaking down the infrared light from rogue gas giants into spectra, astronomers can identify molecular signatures with high precision. This reveals not just what the atmosphere is made of, but how heat moves through it. Vertical temperature gradients, cloud layers, and chemical imbalances all leave signatures in the spectrum. These details help scientists understand how gas giant atmospheres behave without constant input from a star. One important aspect of JWST observations is that they remove a major complication present in starbound planets. In normal exoplanet studies, stellar activity can contaminate measurements. Star spots, flares, and variability can distort planetary signals. Rogue gas giants eliminate that problem entirely. The data comes from one object and one object only. This makes interpretation more straightforward and reduces uncertainty. Another reason rogue gas giants attract attention is that they provide a glimpse into the lower limits of planetary heat retention. By studying objects of different masses and ages, astronomers can track how quickly planets cool once they are isolated. This informs models not just of rogue planets, but of all gas giants. Understanding how long planets retain heat affects estimates of internal structure, atmospheric circulation, and magnetic field longevity. Despite their size, rogue gas giants are still extremely hard to find. Even with infrared telescopes, they are faint. Surveys must cover large areas of the sky repeatedly to identify moving objects against a background of stars and galaxies. Motion is a key clue. Rogue planets move relative to background stars, and careful tracking can reveal this motion over time. This is slow work, requiring years of data and careful analysis. As surveys improve, the known population of rogue gas giants continues to grow. Each new detection strengthens the case that these objects are not rare accidents, but a natural and common outcome of planetary formation. Their presence fills a gap between stars and smaller rogue planets, acting as anchors for understanding the full range of planetary masses that exist without stars. What makes them especially striking is not just their size, but their persistence. Even in deep space, far from any source of external energy, they continue to glow faintly, driven by processes locked inside them since birth. They carry that energy across interstellar distances, marking their paths not with light visible to human eyes, but with infrared signatures that modern instruments are only now able to detect consistently. Rogue gas giants, the frozen behemoths. As more rogue gas giants were detected, astronomers began realizing that these objects were not just leftovers from broken systems, but key pieces in understanding how planetary mass is distributed across the galaxy. Jupiter mass and super-Jupiter rogues carry enormous amounts of material. When added together across the Milky Way, their combined mass is significant enough to affect calculations of galactic structure. These planets do not shine like stars, but gravity does not care about light. Every rogue gas giant contributes mass to the galaxy, altering how matter is spread through the disk and halo. One of the most important discoveries about these planets is how long they can remain detectable. Internal heat retention is not a minor feature. It defines their entire observational lifespan. During formation, gas giants convert gravitational energy into heat as they collapse and grow. This heat becomes trapped beneath thick atmospheric layers composed mainly of hydrogen and helium. These gases are excellent insulators. Heat escapes slowly, over timescales measured in billions of years rather than millions. Super-Jupiter rogue planets cool even more slowly. Their greater mass creates stronger gravitational compression in their interiors, raising internal temperatures and pressures. This allows them to glow faintly in infrared for far longer than Jupiter-mass planets. In practical terms, this means that older super-Jupiter rogues can still be detected when smaller planets have already faded into near invisibility. This detection bias explains why many early rogue planet catalogues were dominated by massive objects. The internal heat of rogue gas giants does not escape evenly. Convection currents transport energy upward through the atmosphere, creating temperature gradients that shape cloud formation and atmospheric circulation. Without stellar heating, these processes are driven entirely from below. This leads to atmospheric behavior that differs from star-bound gas giants. There is no permanent day side or night side. Instead, temperature variations are global and slow, governed by internal dynamics rather than external radiation. Infrared observations reveal this complexity. Spectral data shows absorption features caused by molecules such as methane, water vapor, carbon monoxide, and ammonia. The presence and relative strength of these features change with temperature and pressure, allowing astronomers to estimate not just surface conditions but deeper atmospheric layers. Some rogue gas giants show signs of thick cloud decks that obscure deeper regions, while others appear relatively clear, offering direct views into warmer interior layers. The faint infrared glow of these planets is not uniform across wavelengths. Different wavelengths probe different depths of the atmosphere. Shorter infrared wavelengths emerge from higher, cooler layers, while longer wavelengths escape from deeper, warmer regions. By observing across a wide infrared range, astronomers can reconstruct vertical temperature profiles. This technique has turned rogue gas giants into testbeds for atmospheric physics, free from the complicating influence of nearby stars. James Webb Space Telescope observations have elevated this field dramatically. JWST's sensitivity allows it to detect subtle spectral features that were previously lost in noise. It can observe rogue gas giants at temperatures approaching those of the coldest known substellar objects. This pushes observations closer to the true average rogue gas giant, not just the youngest or most massive examples. With JWST, planets that were once classified as undetectable become accessible. JWST also enables precise measurements of atmospheric composition. Ratios of carbon to oxygen, the presence of heavy elements, and the abundance of specific molecules provide clues about how these planets formed. Gas giants that formed in planetary disks inherit chemical signatures from those disks. If rogue gas giants formed like stars, their compositions would differ. Early JWST results favor planetary disk formation for many rogue gas giants, strengthening the case that they are ejected planets rather than failed stars. This has direct implications for classification. Super-Jupiter rogues occupy a narrow mass range that overlaps with brown dwarfs, but their atmospheric chemistry often aligns more closely with giant exoplanets. This reinforces the idea that formation pathway, not just mass, is crucial. Rogue gas giants become evidence that massive planets can be produced efficiently and expelled just as efficiently without transitioning into stellar objects. Another important aspect is age distribution. By comparing observed temperatures with cooling models, astronomers can estimate how long these planets have been isolated. Some rogue gas giants appear to have been drifting for hundreds of millions of years. Others may have been ejected recently, still retaining significant heat. This age spread indicates that planetary ejection is not confined to early system formation. It can occur long after disks dissipate, triggered by delayed instabilities or external gravitational interactions. The movement of rogue gas giants through the galaxy also matters. Their velocities reflect the dynamics of their ejection. Some travel relatively slowly, remaining near their birth regions. Others move rapidly, crossing large sections of the galactic disk. Over time, this mixing spreads rogue planets throughout the Milky Way, making them a truly galactic population rather than a localized phenomenon. These planets do not interact strongly with interstellar material. Their cross-sections are small and space is sparse. Collisions are effectively non-existent. As a result, rogue gas giants preserve their structure over immense timescales. They are not eroded or altered significantly by their environment. What changes is internal, driven by cooling and contraction. The persistence of magnetic fields is another area of interest. Many gas giants generate magnetic fields through the movement of conductive materials in their interiors. For rogue gas giants, the longevity of these fields depends on how long internal heat drives convection. Models suggest that massive rogues could maintain magnetic fields for billions of years. These fields would interact weakly with the interstellar medium, but they represent ongoing internal activity long after stellar ejection. The study of rogue gas giants also feeds back into understanding starbound planets. Observations of isolated atmospheres help refine models used to interpret exoplanet data. When astronomers observe a gas giant orbiting a star, separating planetary signals from stellar influence is difficult. Rogue planets provide a baseline. They show what a gas giant looks like without irradiation, allowing scientists to isolate the effects of stellar heating when comparing to starbound counterparts. Detection strategies continue to evolve. Wide-field infrared surveys are increasingly combined with motion tracking to identify candidates. Objects that move relative to background stars over months or years are flagged for follow-up. This method is slow but effective. Each new rogue gas giant added to catalogues improves statistical understanding of their population and properties. JWST is not the endpoint. Future missions designed specifically for microlensing and infrared surveys will extend detection limits further. These missions will detect older, colder rogue gas giants that JWST can only study after initial identification. The goal is to build a complete census spanning the full range of masses and ages. Rogue gas giants also influence how astronomers think about the boundaries of planetary systems. The traditional picture of a system ending at its outermost bound planet is incomplete. Systems have histories that include lost members now roaming independently. Every rogue gas giant detected represents a system that once had more structure than it does today. These planets do not fade into insignificance just because they lack stars. Their mass, heat, and persistence make them enduring components of the galaxy. They reshape estimates of how much planetary material exists overall. They challenge assumptions about stability and permanence. They force planetary science to extend beyond the comforting geometry of orbits and into the broader, less predictable architecture shaped by gravity alone. Rogue gas giants remain frozen in the sense that they receive no stellar warmth, but they are not dead. Their faint infrared glow is evidence of ongoing internal processes, slow and relentless, continuing long after their ejection. As instruments grow more sensitive, these behemoths emerge not as rare anomalies, but as one of the dominant forms of planetary existence in the Milky Way, carrying the signatures of formation, instability, and survival across deep space without ever returning to the systems that created them. Internal heat that never fully dies. When astronomers first started taking rogue planets seriously as physical worlds rather than failed stars or drifting debris, the biggest assumption was simple and brutal. Without a star, a planet freezes solid and stays dead forever. That idea did not survive long once the physics was examined closely, because planets do not rely entirely on stars for heat, and in some cases, the heat generated inside a planet can persist for billions of years, even in total darkness. Every rocky or icy planet forms with radioactive elements locked deep inside its interior. Isotopes such as uranium-238, thorium-232, and potassium-40 are created in earlier generations of stars and become part of planetary material during formation. These elements decay slowly, releasing heat at a steady and predictable rate. This is not a brief process. Uranium-238 has a half-life of more than 4 billion years. Thorium-232 lasts even longer. That means a planet formed early in the galaxy can still be producing internal heat today, even if it has been drifting through interstellar space for most of its existence. For rogue planets, this matters more than it does for planets bound to stars. On Earth, radioactive decay contributes only part of the planet's heat budget because sunlight dominates surface temperature. On a rogue planet, radioactive decay becomes the primary long-term energy source. The heat moves upward through the mantle by slow convection, eventually reaching the crust and whatever surface layers exist above it. This heat flow is weak compared to starlight, but it is not zero. And over planetary scales, zero versus non-zero is the difference between absolute thermal death and slow geological activity. Models show that an Earth-mass rogue planet with a rocky interior could maintain a subsurface temperature well above absolute zero for billions of years. The surface would still be extremely cold, but temperature rises rapidly with depth. Just a few kilometers beneath the surface, conditions could be radically different from what space telescopes would ever detect. Ice would insulate the interior, trapping heat in the same way glaciers on Earth slow heat loss from the ground beneath them. The thicker the ice layer, the slower the heat escapes. This is where earlier assumptions collapsed. Scientists realized that freezing from the outside does not mean freezing completely. A rogue planet does not cool evenly. It develops a hard frozen shell, while the interior continues to release heat. That shell becomes an insulating blanket, not a death sentence. The physics is the same reason Europa and Enceladus remain active despite their distance from the Sun, except rogue planets replace tidal heating with radioactive decay as the dominant heat source. The amount of heat depends on mass and composition. Larger rocky planets retain heat longer because they have more radioactive material and lose heat more slowly due to lower surface area to volume ratios. A super-Earth rogue planet could remain internally warm far longer than an Earth mass one. Even small rogue planets are not excluded. The heat flow may be weak, but over time it adds up. Heat does not need to be strong to be meaningful, it only needs to be persistent. Astronomers began running thermal evolution models that treated rogue planets not as dead objects, but as slow cooling systems. These models showed that internal temperatures could remain high enough to prevent complete solidification of deep layers for billions of years. That realization changed how scientists thought about atmospheres, because temperature determines whether gases can remain bound or freeze out completely. If heat reaches the base of an atmosphere from below, even faintly, it slows atmospheric collapse. Without internal heat, any atmosphere would freeze and fall to the surface as solid ice. With internal heat, gases can remain mobile, creating pressure gradients that resist total atmospheric loss. The effect is subtle, but in planetary science, subtle effects over billions of years dominate outcomes. Radioactive decay does something else that matters deeply. It drives slow geological activity. Even minimal volcanism can release gases trapped in the interior. On Earth, volcanic outgassing replenishes the atmosphere over geological timescales. On a rogue planet, this process would be far weaker, but not non-existent. Over hundreds of millions of years, small releases add up, especially if the planet is massive enough to retain those gases. This is not speculation based on hope. The math is simple thermodynamics. Heat generation rates are measurable. Cooling rates are calculable. Insulation effects of ice and rock are well understood. When researchers plugged realistic values into these models, the results consistently showed that internal heat cannot be ignored, even for planets abandoned by their stars. This internal heat becomes the foundation for the second critical factor: atmosphere retention, particularly atmospheres dominated by hydrogen. Thick hydrogen envelopes that refuse to collapse. Hydrogen behaves differently from heavier gases. It is light, mobile, and extremely efficient at trapping heat when present in large quantities. In planetary formation, hydrogen is the most abundant element available. Gas giants capture it easily, but even smaller planets can acquire hydrogen envelopes early in their formation, especially if they form quickly before the surrounding protoplanetary disk disperses. When a planet becomes a rogue, the immediate assumption is that hydrogen escapes into space. That is not always true. Escape depends on temperature, gravity, and time. Without starlight, atmospheric escape slows dramatically. Ultraviolet radiation from a star is the primary driver of hydrogen loss. Remove the star, and you remove the most aggressive stripping mechanism. This flips the expectation. Rogue planets may actually retain hydrogen more effectively than planets orbiting close to stars. The atmosphere becomes cold and stable rather than heated and blown away. If the planet is massive enough, hydrogen does not escape easily. Instead, it settles into a dense, thick envelope surrounding the planet. Hydrogen is an exceptional greenhouse gas under the right conditions. Not in the same way as carbon dioxide or methane, but through collision-induced absorption. When hydrogen molecules collide under pressure, they temporarily form dipoles that absorb infrared radiation. This process becomes significant only at high pressures, exactly the conditions expected in a thick hydrogen atmosphere. This means a hydrogen-rich rogue planet can trap its own internal heat extremely efficiently. The atmosphere acts like a thermal blanket, slowing heat loss from the interior and raising surface temperatures far above what would otherwise be possible. Models show that even a planet with minimal internal heat can maintain surface temperatures far higher than expected if it has a sufficiently thick hydrogen envelope. This was one of the most disruptive ideas introduced into rogue planet research. It suggested that isolation does not automatically mean extreme cold at the surface. A rogue planet with a hydrogen atmosphere could have surface temperatures comparable to icy moons in the outer solar system, or warmer, depending on mass and atmospheric thickness. The thickness matters enormously. A hydrogen envelope just a few % of Earth's mass could create surface pressures hundreds of times greater than Earth's atmosphere. Under those conditions, hydrogen becomes optically thick in the infrared. Heat cannot escape easily. The planet cools slowly, not rapidly. The atmosphere becomes a long-term energy storage system rather than a transient layer. This also changes observational expectations. A hydrogen-rich rogue planet does not appear completely dark. It emits faint infrared radiation due to retained heat. This is why many rogue planets are detected not by reflected light, but by their own weak glow. That glow is not residual formation heat alone. It is heat trapped and recycled by atmospheric physics. Hydrogen envelopes also protect the planet from external space conditions. Cosmic rays and interstellar radiation interact with the upper atmosphere, but much of the energy is absorbed long before reaching the surface. The deeper layers remain shielded and thermally stable. The atmosphere becomes both insulation and armor. Not all rogue planets will have hydrogen envelopes. Smaller rocky planets likely lose most of their hydrogen early, unless they form quickly or are unusually massive. Gas giants and ice giants, however, are almost guaranteed to retain thick hydrogen layers. These planets dominate the known rogue population. Microlensing surveys suggest that Jupiter mass rogues may be extremely common, possibly more common than stars in the Milky Way. For these planets, atmosphere retention is not a question of possibility, but of degree. How thick is the envelope? How much heat is trapped? How slowly does the planet cool? These are quantitative questions now, not speculative ones. What changed the conversation was the realization that hydrogen does not need a star to function as an atmospheric blanket. It only needs pressure and time. Rogue planets have both. They drift slowly. They cool slowly. Their atmospheres evolve over billions of years, not millions. This reframes isolation. A rogue planet is not exposed in the way once imagined. It is wrapped in its own retained gases, heated from within, evolving quietly in the dark. The absence of a star removes one energy source, but it also removes the main mechanism that strips atmospheres away. Subsurface oceans beneath the frozen shell. Rogue planets are not just cold rocks drifting in space. Beneath their frozen exteriors, some may harbor liquid layers sustained entirely by internal heat. This idea emerged from models originally developed for icy moons, like Europa and Enceladus. But the physics scales to rogue planets of sufficient mass. The key is balancing heat generation against insulation. Even without starlight, radioactive decay and residual formation heat can warm interiors enough to maintain a subsurface ocean trapped beneath kilometers of ice. For Earth-mass rogue planets, the ice shell is thick, but the heat flow from the core, while weak, can prevent the entire interior from freezing solid. Heat rises slowly through the mantle and into lower layers of ice. Pressure at depth raises the melting point of water, allowing liquid pockets to exist even when the surface is hundreds of degrees below freezing. The oceans are isolated, dark, and pressurized. They are environments where the physics of convection, heat transfer, and even chemical interactions continue unabated, insulated from cosmic radiation and stellar influence. Ice layers act as insulators and thermal blankets, slowing heat loss and maintaining these liquid interiors over billions of years. In larger rogue planets, thick hydrogen or helium atmospheres above the ice layer provide additional pressure and insulation. The combination of internal heat, high pressure, and insulation makes subsurface oceans not just possible, but likely in certain classes of rogue planets. These oceans are predicted to be chemically active, with salts and minerals leached from the surrounding rock. Pressure and heat together create convective currents within the liquid, preventing total stagnation. The structure is layered: a dense core, possibly rocky or metallic, a mantle that may contain partial melts or convecting ice, a liquid ocean, and a surface frozen shell. The thickness of each layer depends on the planet's mass, composition, and age. The concept of subsurface oceans also expands the range of observable phenomena. Even if the planet is too cold to radiate strongly in infrared at the surface, internal activity may produce detectable signatures. For example, heat escaping through cracks or weak points in the ice can create faint thermal anomalies, potentially observable with sensitive instruments. Models show that larger, younger rogue planets with thick ice layers are the most promising targets. While liquid water is not guaranteed on every rogue planet, the physics strongly suggest that any planet with sufficient mass, heat, and insulating layers has a high probability of maintaining at least small pockets of liquid beneath the surface. Even small differences in radioactive element abundance or initial internal heat can drastically alter ocean size and longevity. These oceans are not stable forever, they gradually cool, but the timescales are immense. For planets ejected early in the galaxy's history, they could persist for billions of years, long enough to create environments with complex chemical cycles entirely independent of stars. Detecting these features directly remains one of the greatest observational challenges in planetary science. Rogue planets do not emit visible light and are often faint even in infrared. Astronomers rely on indirect methods, with instruments designed to detect heat, motion, or chemical signatures rather than optical reflection. Microlensing remains the primary tool for discovering the planets themselves. By monitoring millions of background stars, microlensing events can reveal mass, distance, and occasionally hints of atmospheric structure. Infrared telescopes like the James Webb Space Telescope have opened new windows for studying rogue planet atmospheres. JWST can detect faint thermal emissions, measure spectra to identify hydrogen or methane in envelopes, and determine temperature gradients. These data reveal whether a planet has retained its hydrogen layer or if it is cooling too quickly to support a thick atmosphere. Observations focus on both young rogue planets, which glow more brightly, and older ones, to understand how atmospheres evolve over time. Future missions aim to extend sensitivity to cooler, older rogue planets. Space-based infrared surveys can detect objects too faint for ground-based telescopes. By combining long-duration monitoring with precise spectroscopy, astronomers hope to identify thermal anomalies hinting at subsurface oceans or active geology. Even without direct imaging, variations in infrared flux can indicate heat escaping from beneath ice layers or atmosphere-driven circulation. Ground-based surveys complement these efforts. Instruments equipped with adaptive optics can monitor motion and brightness changes of nearby rogue planets, providing data on rotation rates, atmospheric dynamics, and possibly surface features through thermal mapping. While direct evidence of subsurface oceans is currently impossible, these observations constrain models by measuring heat flux and atmospheric composition. Isolation while still orbiting a star. Ultra-wide orbit planets exist in a category that feels almost contradictory. They are not rogue planets, they still orbit a star. They are gravitationally bound. Yet in every physical, thermal, and environmental sense, they live closer to interstellar space than to the stellar systems they belong to. These are planets so distant from their parent stars that the concept of a solar system begins to break down. Their orbits stretch so far that the star becomes little more than a bright point in an otherwise starless sky. Astronomers define ultra-wide orbit planets as planetary mass objects orbiting a star at distances typically greater than several hundred astronomical units, often extending into the thousands of AU. 1 astronomical unit is the distance between Earth and the Sun. Neptune, the outermost major planet in our solar system, orbits at about 30 AU. The Kuiper belt extends to roughly 50 AU. The Oort cloud, a theoretical boundary rather than a planet-hosting region, reaches tens of thousands of AU. Ultra-wide orbit planets exist in the vast emptiness between these familiar scales. At distances of 1000 AU, 2000 AU, sometimes even beyond 5000 AU, the star's gravitational grip becomes extraordinarily weak. The orbital periods stretch into hundreds of thousands or even millions of years. These planets do not experience seasons, solar cycles, or stellar influence in any meaningful way. The star's light is so diluted that it contributes almost nothing to surface temperature or atmospheric dynamics. The energy received from the star is often weaker than the background radiation from the galaxy itself. From a physics standpoint, these planets exist in a gravitational gray zone. They are technically bound to the star, but only barely. A passing star at the right distance, a molecular cloud shockwave, or even slow gravitational tides from the galactic disk can destabilize their orbits. Many astronomers believe ultra-wide orbit planets are transitional objects, halfway between traditional planets and rogue planets, waiting for the right disturbance to push them into full isolation. The discovery of these planets forced scientists to confront uncomfortable questions about how planetary systems form and survive. Traditional models of planet formation rely on protoplanetary disks that extend a few hundred AU at most. Beyond that range, disk material becomes too thin to form planets through standard core accretion. Yet ultra-wide orbit planets clearly exist. Their presence suggests violent histories rather than gentle formation. One leading explanation is gravitational scattering. In young planetary systems, multiple giant planets form close to their star. Their mutual gravitational interactions can be chaotic. When these massive bodies pass near each other, energy is exchanged unevenly. One planet moves inward, tightening its orbit, while another is flung outward at extreme distances. If the ejection velocity is just below escape speed, the planet does not become rogue. Instead, it ends up stranded in an ultra-wide orbit, looping around the star on an elongated, fragile path. These planets often follow highly eccentric orbits. They spend most of their time at extreme distances, only briefly approaching the star before swinging back into darkness. During those distant phases, the star provides no meaningful heat. Surface temperatures approach the same values as rogue planets. Any atmosphere they retain behaves as though the star does not exist. Another formation path involves stellar flybys in dense star-forming regions. Stars are born in clusters, packed closely together. In these environments, gravitational interactions are common. A passing star can disturb a young planetary system, pulling planets outward or capturing planets from neighboring stars. Some ultra-wide orbit planets may not have formed around their current star at all. They may be captured objects, loosely bound during chaotic early encounters. This capture scenario explains why some ultra-wide orbit planets appear mismatched with their host stars. Their compositions, temperatures, and formation timelines sometimes do not align with expectations based on the star's age and metallicity. They behave like foreign bodies that were never meant to be there, barely tethered to a star they did not originate from. The distances involved are staggering. At 1000 AU, light from the star takes nearly 6 days to reach the planet. At 5000 AU, it takes almost a month. At these ranges, the star's gravitational pull is comparable to the influence of nearby stars in the galactic neighborhood. The planet's orbit is not a clean ellipse, shaped only by its star. It is constantly being distorted by the galaxy itself. This makes ultra-wide orbit planets dynamically unstable over long timescales. Simulations show that many of them are temporary residents. Over millions or billions of years, small perturbations accumulate. A close stellar passage nudges the orbit slightly. Galactic tides stretch it further. Eventually, the planet's velocity exceeds escape speed, and it drifts away, becoming a true rogue planet. In this sense, ultra-wide orbit planets are often seen as pre-rogues. Despite this instability, astronomers have confirmed multiple ultra-wide orbit planets through direct imaging, microlensing, and astrometric measurements. These detections are rare not because the planets are rare, but because they are extremely difficult to detect. Their separation from the star makes them faint and slow-moving relative to background stars. Direct imaging works only for young, massive planets that still glow with residual heat. When astronomers do image these worlds, the images are unsettling. The planet appears as a tiny point of light far from the star, separated by an enormous gulf of darkness. There are no neighboring planets, no asteroid belts, no familiar architecture. Just a star and a distant companion, barely connected. Their environments are closer to deep space than to any planetary system. The cosmic microwave background contributes more to their thermal environment than their star. Interstellar dust, cosmic rays, and passing radiation fields dominate their surroundings. The star is no longer the central organizing force. It is simply one influence among many. This extreme isolation has profound consequences for planetary evolution. Atmospheric escape processes slow down because stellar radiation is weak. At the same time, atmospheric replenishment through volcanism or outgassing becomes the dominant factor shaping the atmosphere. Chemistry evolves without photochemical reactions driven by ultraviolet light. Instead, cosmic rays and internal heat drive slow, unusual chemical pathways. Surface conditions are frozen, but not necessarily inert. Internal heat may still exist, especially in massive planets. Gas giants in ultra-wide orbits can retain internal heat for billions of years, glowing faintly in infrared. Their atmospheres circulate slowly, driven by heat from below rather than energy from above. These planets resemble isolated gas giants more than traditional exoplanets. Rocky, ultra-wide orbit planets, if they exist, would be even lonelier. Their surfaces would be permanently frozen. Any subsurface activity would be hidden beneath thick ice layers. Without tidal heating or stellar input, only radioactive decay would power internal processes. They would exist in near-complete darkness, with their star barely distinguishable from the surrounding field of stars. The phrase barely gravitationally bound is not an exaggeration. At extreme distances, the gravitational binding energy between planet and star is minuscule. A slow interaction can unbind the system. This makes ultra-wide orbit planets sensitive indicators of galactic environment. Their survival depends not just on their star, but on the density of nearby stars, the motion of the star through the galaxy, and the gravitational landscape of the Milky Way itself. In some cases, astronomers have identified planetary mass companions at distances so great that debate arises over whether they should even be called planets. At thousands of AU, the distinction between planet, brown dwarf, and stellar companion becomes blurred. Classification depends not only on mass, but on formation history, which is often unknown. This has fueled ongoing debate about how to define planetary systems at extreme scales. What makes these orbits especially haunting is their silence. Unlike close-in planets that transit their stars or produce detectable wobbles, ultra-wide orbit planets leave almost no signature. They move slowly. Their gravitational influence is weak. Many may remain undetected forever, drifting quietly at the edge of stellar influence. Yet their existence reshapes how astronomers think about planetary systems. A system is no longer a tight arrangement of worlds clustered near a star. It can extend across vast distances, blending into the galactic environment. The boundary between being part of a system and being alone becomes fuzzy. Ultra-wide orbit planets show that isolation is not binary. A planet does not need to be fully rogue to be alone. It can remain technically bound while living in conditions indistinguishable from interstellar space. These planets orbit stars they rarely feel, in systems that barely hold together, waiting for the slightest push to send them drifting into the dark. What makes ultra-wide orbit planets truly unsettling is not just distance, but time. Time behaves differently at these scales. A planet orbiting at several thousand astronomical units does not complete an orbit in decades or centuries. It takes hundreds of thousands, sometimes millions of years to complete a single revolution around its star. Civilizations could rise and fall on Earth many times over before such a planet moves noticeably along its path. From any practical perspective, the orbit is almost static. This extreme slowness creates a form of isolation that is rarely discussed. These planets are not dynamically active members of a planetary system. They do not participate in resonances. They do not exchange angular momentum with inner planets. They do not shape asteroid belts or influence debris disks in detectable ways. Their existence is almost irrelevant to the rest of the system, and the system is equally irrelevant to them. From the planet's point of view, the star is no longer a dominant presence. Its brightness is reduced to a fraction of what inner planets receive. At distances beyond 1000 AU, the star appears no brighter than many background stars in the sky. There is no clear sunrise or sunset cycle tied to orbital motion. The star does not meaningfully heat the surface or drive weather. The planet exists in a thermal regime dictated almost entirely by its own internal properties and the ambient environment of the galaxy. This is where the phrase barely gravitationally bound becomes more than a technical description. The gravitational connection between the planet and the star is so weak that it competes with external forces. The Milky Way itself exerts tidal forces on planetary systems as they orbit the galactic center. For close-in planets, these forces are negligible. For ultra-wide orbit planets, they are not. Galactic tides stretch and compress orbits slowly over time. They do not rip planets away instantly, but they distort trajectories, increasing eccentricity and altering orbital inclination. Over millions of years, these small changes accumulate. The planet's orbit becomes more elongated, spending even more time at extreme distances and even less time near the star. Each pass through the inner portion of the orbit becomes weaker and shorter. Passing stars add another layer of instability. The Milky Way is not empty. Stars move relative to one another, occasionally passing within a few thousand AU. For an ultra-wide orbit planet, a stellar flyby at these distances is not a rare catastrophic event. It is a realistic long-term risk. Even a slow, distant pass can inject enough energy into the planet's orbit to unbind it completely. What makes this especially important is that the planet does not need to be struck or closely approached. Gravity acts at a distance. A star passing several thousand AU away can still perturb an orbit that is already fragile. The planet's fate depends on cumulative nudges rather than single dramatic encounters. Over time, the probability of escape approaches certainty. This leads to a critical idea in modern planetary science. Many rogue planets may have once been ultra-wide orbit planets. They were not violently ejected at high speed. They drifted outward, lingered on the edge of a system for eons, and were eventually peeled away by the galaxy itself. Isolation while orbiting a star may be a temporary phase rather than a stable endpoint. Observational evidence supports this view. Surveys show a population of wide-orbit planetary mass objects whose binding energies are extremely low. Their velocities relative to their stars are just below escape speed. They appear balanced on a knife edge. Small uncertainties in measurement sometimes determine whether an object is classified as bound or free-floating. This uncertainty is not just observational error. It reflects the physical reality of their situation. Detecting these planets requires different methods than those used for close-in exoplanets. Transit methods are useless at such distances. Radial velocity signals are too weak. Astronomers rely on direct imaging and long baseline astrometry. Direct imaging captures faint infrared light from young or massive planets still retaining internal heat. Astrometry tracks slow motion across the sky over years or decades, revealing whether the planet shares the star's motion through space. Even when detected, confirming that a planet is truly bound is difficult. At thousands of AU, orbital motion is so slow that a few years of data barely show curvature. Astronomers must infer binding from shared proper motion and statistical likelihood, rather than direct orbital measurement. This adds uncertainty and fuels debate over classification. Some ultra-wide companions sit right at the boundary between planet and brown dwarf. Their masses fall near the deuterium burning limit. At close distances, formation history might clarify their nature. At extreme distances, formation history is often unknowable. Did the object form in a disk and scatter outward, or did it form like a star and simply end up small? The distance blurs these distinctions. This ambiguity has forced astronomers to rethink what orbiting a star truly means. At extreme separations, the system no longer behaves like a planetary system. It behaves more like a loose binary, or even a transient pairing. The classical image of planets circling stars in neat, hierarchical systems collapses under these conditions. From a physical standpoint, ultra-wide orbit planets experience environments closer to rogue planets than to traditional exoplanets. Their atmospheres, if they have them, evolve without stellar input. Their temperatures are set by internal heat and background radiation. Their chemical processes proceed slowly, driven by cosmic rays rather than ultraviolet light from the star. In practical terms, the star might as well not exist. Yet the gravitational link, however weak, still matters. It defines the planet's long-term trajectory through the galaxy. A bound planet follows its star around the Milky Way. A rogue planet follows its own independent path. That difference affects encounter rates with other stars, exposure to dense regions of the galaxy, and long-term survival. Even the weakest bond can shape destiny over cosmic timescales. This is what makes these orbits the loneliest ever discovered. The planet is not free, yet not truly part of anything. It belongs to a system that barely acknowledges it. It orbits a star that does not warm it, light it, or shape its environment. Its future is uncertain, its past often violent, and its present defined by isolation measured not just in distance, but in influence. Ultra-wide orbit planets exist at the edge of what planetary systems can be. They mark the boundary where order gives way to drift, where gravity loosens its grip, and where planets begin the long transition from belonging to wandering. 2MASS J 2126 8140b, the widest orbit planet known. 2MASS J 2126 8140b exists at a distance so extreme that calling it an orbit almost feels misleading. The object circles its host star at roughly 7,000 astronomical units. That number is not abstract. 7,000 AU places the planet far beyond anything traditionally considered part of a planetary system. At that separation, the star's gravity is no longer a dominant force shaping daily or even long-term conditions. It is a weak tether stretched across deep space. To put the scale in context, Neptune orbits at about 30 AU. The Kuiper belt fades out around 50 AU. The hypothetical inner edge of the Oort cloud begins thousands of AU away. 2MASS J 2126 8140b does not sit near the edge of this region. It lives deep within it. If this planet existed in our solar system, it would not appear as a member of the planetary family. It would look like a separate object, barely associated with the Sun at all. At a distance of around 7,000 AU, light from the host star takes more than 40 days to reach the planet. The star is not a sun in any meaningful sense. It is a distant point of light among many others. Its heat contribution is effectively zero. Any warmth this planet has comes from within, not from above. The orbital period reflects this extreme separation. One full orbit around the star takes close to 1 million years. That means this planet has completed very few orbits since complex life emerged on Earth. In human terms, the orbit is almost frozen. Motion exists, but it unfolds on timescales that erase any sense of a system in motion. The discovery of 2MASS J 2126 8140b did not come from traditional planet hunting methods. There was no transit, no detectable stellar wobble, no periodic signal. Instead, it emerged from wide-field infrared surveys designed to catalogue faint, cool objects in the solar neighbourhood. The 2-micron all-sky survey, known as 2MASS, had already revealed countless low-mass stars and brown dwarfs. This object stood out because of its brightness, temperature, and motion through space. Astronomers noticed that 2MASS J 2126 8140b shared nearly identical motion with a young, low-mass star located far away from it on the sky. Proper motion measurements showed that both objects drifted together through the galaxy. This was not coincidence. The odds of two unrelated objects moving in lockstep at the same speed and direction were extremely small. Further analysis revealed that the separation between the two was vast, but not infinite. Gravitational models showed that despite the distance, the object could still be bound. Barely. The binding energy was incredibly low, but mathematically non-zero. That single detail pushed the object across the classification boundary from rogue planet to bound companion. From the moment those calculations were published, controversy followed. The headlines did not focus on technical nuance. They went straight to the implication: planet found barely attached to its star. That phrasing was not exaggeration. It was a literal description of the system's dynamics. Astronomers debated whether the word orbit even applied. At 7,000 AU, The gravitational influence of passing stars and the tidal field of the Milky Way are comparable to the pull of the host star. The planet's path is not a clean ellipse defined solely by two bodies. It is constantly perturbed, stretched, and reshaped by external forces. The discovery forced researchers to confront an uncomfortable reality. If this object is considered a planet, then the definition of planetary systems must stretch far beyond anything previously accepted. If it is not considered a planet, then mass alone is not enough to define one. The debate exposed how fragile existing classifications were when pushed to extremes. 2 Mass J 2126-8140b has a mass estimated to be several times that of Jupiter. It is not a small object. It retains internal heat and glows faintly in infrared wavelengths. That glow made it detectable despite its isolation. Yet its mass also raises questions. At such distances, did it really form in a disk around its star, or did it form independently and later become weakly bound? Many astronomers favor a scattering scenario. In the early life of the system, gravitational interactions may have flung the object outward at nearly escape velocity. It did not leave the system entirely. Instead, it stalled at the edge, where gravity slowed it just enough to keep it from drifting away. The result is an object balanced on the threshold between bound and free. Others suggest a capture scenario. In dense star-forming regions, stars pass close enough to exchange companions. A planet or brown dwarf formed around one star can be stripped and loosely captured by another. At 7000 AU, capture becomes more plausible than disk formation. The object's wide separation fits this picture disturbingly well. What makes 2 Mass J 2126-8140b especially important is not just its distance, but its stability, or lack of it. Simulations show that even a modest stellar flyby could unbind the planet. The system does not need a catastrophic event. A slow, distant encounter over thousands of years could be enough to break the gravitational tie. This is why many astronomers describe it as a rogue in waiting. It has not escaped yet, but nothing guarantees it will remain bound. Over millions or billions of years, the odds favor separation. The galaxy is not static. Stars move. Encounters happen. Tidal forces accumulate. The planet's future is uncertain by definition. From a physical standpoint, the planet already behaves like a rogue. Its atmosphere, temperature, and internal processes are independent of the star. Its environment is shaped by interstellar conditions rather than stellar radiation. The only difference between this planet and a true rogue is a faint gravitational thread that could snap at any time. This discovery shifted how astronomers think about planetary isolation. It demonstrated that loneliness does not begin only after ejection. A planet can be effectively alone while still orbiting a star. The star can be present yet irrelevant, bound yet powerless. 2. Mass J 2126-8140b stands as a boundary case, not just in distance, but in concept. It occupies a region where planetary science overlaps with stellar dynamics and galactic structure. Its existence suggests that planetary systems are not neatly bounded arrangements, but messy, extended structures that blur into interstellar space. This object did not just extend the known limits of planetary orbits. It forced astronomers to accept that the transition from planet to rogue is not a single moment. It can be a slow drift, measured in millions of years, beginning long before the final separation ever occurs. 2. Mass J 2126-8140 BE, the widest orbit planet known. What truly unsettles astronomers about 2 Mass J 2126-8140b is not just how far away it is, but how fragile its connection to its star appears when examined over cosmic timescales. At a separation of roughly 7,000 astronomical units, the planet does not reside in a stable gravitational well. It sits in a region where gravity is weak, diffuse, and constantly contested by forces beyond the system itself. At this distance, the star's gravitational pull is only marginally stronger than the background gravitational influence of the Milky Way. The planet's orbit is not governed solely by a two-body interaction. Galactic tides, the collective gravity of the galaxy's disk, and the slow passage of nearby stars all play measurable roles. This makes the orbit fundamentally unstable in the long term, even if it appears bound today. Computer simulations that model the future of the system show a consistent pattern. The orbit slowly stretches. Eccentricity increases. The planet spends more and more time at extreme distances, drifting far from the star before briefly falling back inward. Each orbit becomes more distorted than the last. The binding energy decreases with every external perturbation, even if those perturbations are small. A single close stellar flyby is not required. The planet does not need a dramatic encounter to escape. Instead, many small gravitational nudges accumulate over time. A star passing several thousand AU away may slightly alter the planet's velocity. The effect is subtle, but not reversible. Over millions of years, these changes compound, pushing the planet closer to escape speed. This is why many astronomers hesitate to describe 2 mass J2126-8140b as a stable planet. Its status is conditional. It is bound only under the present configuration of the galaxy. Change the local stellar density, the star's galactic orbit, or the timing of future encounters, and the outcome shifts. The planet's fate is probabilistic rather than deterministic. This uncertainty fueled intense debate when the discovery was announced. Some researchers argued that labeling it a planet stretched the term beyond usefulness. Others countered that mass and current gravitational binding should be sufficient. The disagreement was not semantic. It exposed a deeper issue in planetary science. Definitions had been built around compact systems, not extended ones. Media coverage seized on this ambiguity. Headlines emphasized instability rather than classification. Planet found barely attached to its star captured public attention because it reflected the underlying physics. The word barely was not exaggeration. It was a precise description of the binding energy involved. Follow-up studies examined whether the object could even survive its current orbit over the age of the system. The answer was uncomfortable. Models suggest that over a few 100 million to a few billion years, the likelihood of escape becomes significant. The planet is young by astronomical standards, which may explain why it is still bound. Age in this case is protection. Time is the enemy. Another factor complicating the picture is the environment in which the system formed. Young stars often originate in clusters where stellar density is high. If 2 mass J 2126-8140b formed during such a phase, early interactions could have already reshaped its orbit dramatically. What we observe today may be the remnant of a far more chaotic past. Some astronomers argue that the planet was never meant to remain bound. It may have been ejected early and only temporarily slowed enough to linger near the star. Others suggest it was captured during a brief gravitational encounter in the cluster. In both scenarios, long-term stability is not expected. The system appears transitional rather than settled. This perspective reframes the object entirely. Instead of being an outlier planet with an unusually wide orbit, it becomes a snapshot of a process in motion. It represents a stage between belonging and isolation. The planet has not yet crossed the line into full rogue status, but it is no longer a functional member of a planetary system. From a physical standpoint, the planet already lives like a rogue. Its atmospheric evolution, internal heat loss, and chemical processes operate without stellar input. The star does not drive weather, photochemistry, or climate. The planet's surface conditions are dictated by internal energy and interstellar radiation fields, not by orbital distance in any practical sense. This disconnect between dynamical status and physical reality is what makes 2 mass J 2126-8140b so important. It shows that orbiting a star does not guarantee relevance. A planet can remain bound, yet be functionally independent, evolving as though it were free-floating. The system also provides a testing ground for understanding how many rogue planets form through slow unbinding rather than violent ejection. If objects like this are common, then the population of rogue planets may include many former wide-orbit companions that drifted away over time. The galaxy may be filled with planets that once had stars, lost them quietly, and left no obvious trace of their origins. Observationally, two Mass J 2126 8140b challenges detection strategies. Its extreme separation makes it easier to image directly, yet harder to confirm as bound. Astronomers must rely on precise measurements of motion and distance, often pushing instruments to their limits. Long-term monitoring is required, spanning years or decades to refine its trajectory. As more ultra-wide companions are discovered, patterns are emerging. Many occupy similarly fragile orbits. Many exist around young stars. Many have masses near the boundary between planets and brown dwarfs. Together, they suggest that extreme isolation while orbiting a star may be more common than previously thought. HIP 65426b, J. West's famous isolated target. HIP 65426b entered astronomy in a way very few exoplanets ever do. Not as a faint signal hidden in data, not as a statistical blip inferred from motion, but as an actual visible world, directly imaged, clearly separated from its star, hanging alone in the darkness. From the moment it was confirmed, it became a reference point for what isolation looks like when a planet is still technically part of a stellar system. HIP 65426b orbits a young hot star located about 385 light-years from Earth. The star itself is massive, bright and fast rotating, the kind of star that usually makes planet detection difficult because its glare overwhelms nearby objects. Yet this planet was not nearby. It sat far out, at a distance of roughly 92 astronomical units. That alone made it unusual. This is more than 3 times farther than Neptune's orbit around the Sun, well beyond the region where most planets detected by direct imaging reside. At that distance, the planet does not behave like a typical exoplanet. Stellar radiation is weak, orbital motion is slow. The star's gravity dominates only in the most basic sense. HIP 65426b exists in a region where the system transitions from structured planetary space into something closer to the outskirts of stellar influence. It is not an ultra-wide orbit object like two Mass J 2126 8140b, but it occupies a middle ground that is equally revealing. The planet was discovered through direct imaging using the SPHERE instrument on the Very Large Telescope in Chile. This was not accidental. The system had been selected specifically because the star was young, meaning any massive planets would still be warm from formation and glowing in infrared light. HIP 65426b delivered exactly that. It appeared as a bright, isolated point far from the star, clearly detached from the glare that hides closer planets. This distance is a major reason HIP 65426b became so important. At around 92 AU, it sits far enough away to be resolved cleanly, but close enough to still be considered part of a recognizable planetary system. That makes it ideal for atmospheric study. The planet is isolated enough to be seen clearly, yet not so distant that its origin becomes impossible to interpret. From the beginning, astronomers suspected that HIP 65426b did not form where it currently resides. At nearly 100 AU, standard core accretion models struggle. Protoplanetary disks become thin and unstable at those distances. There is not enough solid material to build a massive planetary core efficiently. The more likely explanation is that the planet formed closer in and was scattered outward through gravitational interactions with other massive bodies early in the system's history. That scattering scenario fits the planet's current isolation. It suggests a violent past. Chip 65426b may be the survivor of an early dynamical reshuffling, thrown outward while other planets moved inward or were ejected entirely. The fact that no other massive planets have yet been detected closer in does not contradict this. They may exist but be harder to see, or they may already be gone. HIP 65426b itself is massive, estimated at roughly 6 to 12 times the mass of Jupiter. This mass allows it to retain internal heat for a long time. Even though stellar heating is weak at its orbit, the planet glows strongly in infrared wavelengths due to residual heat from formation. This glow is what made it such a perfect target for direct imaging and later for JWST. When the James Webb Space Telescope began its science operations, Chip 65426b quickly rose to the top of the target list. JWST was built to study faint infrared sources with unprecedented sensitivity and spectral resolution. HIP 65426b offered a rare combination: brightness, separation, youth, and isolation. It was one of the cleanest laboratories available for testing JWST's ability to analyze exoplanet atmospheres. JWST observations revealed details that had previously been inaccessible. The planet's atmosphere showed strong signatures of water vapor and carbon monoxide. These molecules absorb infrared light in distinct patterns, allowing scientists to identify them with high confidence. The data also suggested the presence of thick clouds, likely composed of silicates and iron droplets suspended high in the atmosphere. The atmosphere is hot, with temperatures estimated around 1,300 to 1,600 degrees Kelvin. This heat drives complex atmospheric circulation, even in the absence of strong stellar forcing. Unlike close-in planets where starlight dominates weather patterns, HIP 65426b's atmosphere is powered primarily by internal heat rising from below. This makes it an important comparison object for isolated gas giants and even rogue planets. The isolation plays a key role here. Because the planet is far from its star, photochemical reactions driven by ultraviolet radiation are weaker than they would be closer in. This simplifies atmospheric chemistry in some ways, allowing scientists to study baseline processes without extreme stellar interference. It becomes easier to isolate the effects of temperature, gravity, and composition. JWST spectra were remarkably clean. The planet's separation from the star reduced contamination, making it possible to extract atmospheric data with high precision. This is exactly why JWST focused on HIP 65426b early in its mission. It served as a benchmark, a test case for how well the telescope could characterize directly imaged exoplanets. The first JWST images of HIP 65426b spread quickly beyond scientific circles. Media outlets emphasized the clarity of the image and the loneliness of the planet. Headlines highlighted how far it sat from its star and how clearly it could be seen. For the public, this was not an abstract detection. It was a picture of a world, visibly alone, glowing in deep space. The planet's isolation became a central theme in coverage. Articles described it as a massive world drifting on the outskirts of its system, barely connected to its star. While technically still bound, it was portrayed as living in near interstellar conditions. This framing resonated because it aligned with what the image showed: a bright point far removed from the central star, separated by a wide gulf of darkness. Within the scientific community, the reaction was more focused. The images validated JWST's capabilities almost immediately. They demonstrated that detailed atmospheric spectroscopy of directly imaged planets was not only possible, but practical. HIP 65426b became a proof-of-concept target, showing what the next decade of exoplanet science could look like. The planet's unusual distance also raised renewed interest in how common such isolated orbits might be. If a planet like HIP 65426b exists around this star, how many others exist elsewhere, scattered far out, unseen because they are cooler, older, or less massive? Its discovery reinforced the idea that planetary systems are not compact arrangements, but extended, often chaotic structures. HIP 65426b sits in a region where classification begins to blur. It is clearly a planet by mass. It is clearly bound to a star. Yet its environment, energy balance, and atmospheric evolution resemble those of far more isolated objects. It bridges the gap between traditional exoplanets and the lonelier worlds that exist on the edge of stellar influence. That is what made it irresistible to JWST and what made its images so widely shared. HIP 65426b is not just another gas giant. It is a visible example of isolation while still orbiting a star. A planet that shows how distance alone can transform a world into something fundamentally different. HIP 65426b. JWST's famous isolated target. What separates HIP 65426b from many other directly imaged planets is not just how far it sits from its star, but how cleanly it allows scientists to study a planetary atmosphere without interference. Most exoplanets that orbit far from their stars are either too cold, too faint, or too close to background noise to yield high-quality data. HIP 65426b occupies a rare middle zone, where distance becomes an advantage rather than a limitation. At roughly 92 astronomical units, the planet is far enough from its star that stellar glare is significantly reduced, but close enough that the planet remains bright due to its youth and mass. This balance is precisely what made it an ideal target for the James Webb Space Telescope. JWST does not just detect light, it separates light into detailed spectra, breaking it into wavelengths that reveal temperature, pressure, and chemical makeup. For that to work, the signal must be clean. HIP 65426b provided one of the cleanest signals available. JWST's observations went beyond confirming known molecules. They allowed astronomers to probe the vertical structure of the atmosphere. Variations in absorption across wavelengths revealed information about cloud layers, pressure gradients, and temperature changes with altitude. These details are impossible to extract from most exoplanets because stellar contamination overwhelms subtle atmospheric features. In this case, isolation worked in the planet's favor. The planet's atmospheric composition became a point of intense interest. The presence of water vapor was expected, but its abundance offered clues about formation history. Carbon monoxide levels suggested a carbon-to-oxygen ratio consistent with formation in a disk rather than direct collapse. This supports the idea that HIP 65426b formed closer to its star and migrated outward through gravitational interactions. Cloud structure added another layer to the analysis. The data indicated thick, high-altitude clouds composed of silicate particles and possibly iron condensates. These clouds affect how heat escapes from the planet and how light passes through the atmosphere. They create broad absorption features that shape the observed spectrum. Understanding these clouds is critical because similar cloud processes are expected in isolated gas giants and even in some rogue planets. The isolation of HIP 65426b also means its atmosphere evolves under different conditions than close-in planets. Without strong ultraviolet radiation from the star, photochemical reactions are suppressed. This allows heavier molecules to persist without being broken apart as quickly. Atmospheric mixing is driven by internal heat rather than stellar heating, producing circulation patterns more similar to brown dwarfs than hot Jupiters. This similarity is not accidental. In many ways, HIP 65426b behaves like a low-mass brown dwarf that happens to be loosely bound to a star. This overlap is scientifically valuable. Brown dwarfs have been studied for decades, but their formation pathways differ from planets. HIP 65426b provides a bridge between these categories, allowing researchers to test where planetary physics ends and stellar physics begins. JWST's focus on this object was also strategic. Early mission targets needed to demonstrate the telescope's full capabilities quickly. HIP 65426b offered a high probability of success with minimal ambiguity. It became one of the first exoplanets whose atmosphere was characterized in such detail by JWST, setting a standard for future observations. The media response to the JWST images reflected this significance. The images were widely shared not just because they were visually striking, but because they represented a new level of clarity. Headlines emphasized how clearly the planet stood apart from its star, how isolated it appeared, and how detailed the atmospheric data was. The planet was framed as proof that JWST could deliver on its promise. Public reaction often focused on the image itself, a glowing dot separated from a brilliant star by a wide, dark gap. Scientists, however, focused on the spectra. The real breakthrough was not the picture, but the information encoded within the light. Each dip and peak in the spectrum represented molecules, temperatures, and pressures measured across hundreds of light years. Within the scientific community, HIP 65426b quickly became a benchmark. Its atmospheric data are now used to calibrate models of giant planet formation and evolution. Researchers compare it to both close-in gas giants and free-floating planetary mass objects to understand how environment shapes planetary development. The planet's isolation also reinforces a broader trend in exoplanet science. Systems are not neatly arranged. Planets can be scattered far from their stars, occupying regions once thought empty. HIP 65426b shows that these distant worlds are not just curiosities. They are accessible, measurable, and central to understanding how planetary systems evolve. By focusing on HIP 65426b, JWST demonstrated that isolation does not mean invisibility. In fact, isolation can make a planet easier to study, stripping away the complications introduced by intense stellar radiation. This insight is reshaping how astronomers choose targets, shifting attention toward planets that sit far from their stars, where the noise is low and the physics is clearer. Planetary orbits that defy formation models. For decades, planetary formation theory rested on a relatively stable foundation. Planets form in disks of gas and dust surrounding young stars. Material clumps together. Small solids become larger ones. Gravity takes over. Given enough time, planets emerge. This framework works remarkably well for planets close to their stars. It explains the architecture of our solar system and thousands of exoplanetary systems discovered since the 1990s. But it begins to unravel the moment astronomers confront planets on extreme orbits, worlds located tens, hundreds, or even thousands of astronomical units from their stars. At those distances, the standard model of planet formation, known as core accretion, runs into severe and unavoidable physical limits. Core accretion relies on density. It requires a protoplanetary disk thick with solid particles and gas. Dust grains collide, stick together, and grow. Over time, kilometer-sized planetesimals form. These merge into planetary cores, massive enough to gravitationally attract surrounding gas. This process is slow, even under ideal conditions. It requires millions of years, and a steady supply of material. The problem is that protoplanetary disks do not behave uniformly across their entire radius. Density drops sharply with distance from the star. Temperature falls. Collision rates decrease. Beyond a few tens of astronomical units, the disk becomes thin and diffuse. Solid material is spread so far apart that collisions become rare. Growth slows dramatically. At distances beyond 50 or 100 AU, the math stops working entirely. There simply is not enough material, concentrated enough for large planetary cores to form before the disk dissipates. Observations of real disks confirm this. Even the most massive disks observed around young stars show steep density gradients. Gas and dust thin out rapidly with distance. Disk lifetimes are short on cosmic timescales, typically a few million years. Core accretion already struggles to build giant planets at 10 or 20 AU within that window. At 100 AU, it fails outright. At hundreds or thousands of AU, it is physically implausible. Yet planets exist at those distances. This is where the contradiction becomes unavoidable. If planets cannot form there through core accretion, and yet they are found there, something else must be happening. Either the planets formed closer in and moved outward, or they formed through an entirely different mechanism. This realization forced astronomers to reopen formation models that had been considered secondary or even fringe. One such model is disk instability. Unlike core accretion, disk instability does not rely on slow growth through collisions. It operates quickly and violently. In this scenario, a protoplanetary disk becomes massive and cool enough to fragment under its own gravity. Instead of dust grains slowly clumping together, entire regions of the disk collapse directly into planetary mass objects. Disk instability can occur on timescales of thousands of years rather than millions. It does not require the slow buildup of a solid core. It requires only that the disk be massive, cold, and unstable. Under the right conditions, spiral arms form in the disk. These arms concentrate mass. If cooling is efficient enough, sections of the disk collapse, forming objects with masses comparable to gas giants. This mechanism is far more efficient at large distances from the star. The outer regions of disks are cooler. Cooling allows gravitational collapse to proceed. In theory, disk instability could form massive planets directly at tens or even hundreds of AU. This made it an attractive explanation for wide-orbit gas giants discovered through direct imaging. However, disk instability comes with its own limitations. Not all disks are massive enough. Not all disks cool efficiently. Observations suggest that truly unstable disks are rare. Most disks appear stable, especially around lower-mass stars. Even when instability occurs, it often produces objects near the boundary between planets and brown dwarfs, raising questions about classification. There is also the issue of survival. Objects formed through disk instability must avoid rapid inward migration. Gravitational interactions with the disk itself tend to drive massive objects toward the star. Without some stabilizing mechanism, many of these objects would not remain on wide orbits. They would spiral inward or be ejected entirely. Despite these challenges, disk instability remains one of the few mechanisms capable of forming planets far from their stars without invoking later migration. It provides a partial answer, but not a complete one. It can explain some wide-orbit gas giants, particularly around massive stars with equally massive disks. It struggles to explain lower-mass planets or systems where disk conditions do not support fragmentation. The tension between theory and observation has only grown as more extreme systems are discovered. Each new planet found on a distant orbit forces scientists to ask the same question again. Did this planet really form here, or did it arrive later? The failure of core accretion at large distances is not a minor detail. It is a hard boundary imposed by physics. Beyond a certain point, the model does not bend. It breaks. What makes this especially important is that many of the most isolated planets known are also massive. These are not small rocky worlds. They are gas giants, sometimes several times the mass of Jupiter. Their existence at extreme distances magnifies the problem. Forming such massive objects requires either enormous amounts of material or rapid collapse. Core accretion cannot provide either in the outer reaches of disks. As a result, planetary orbits that defy formation models are not just oddities. They expose gaps in our understanding. They reveal that planetary systems are shaped not only by calm, orderly growth, but by instability, migration, and disruption. The further from the star a planet is found, the more likely its history involved violence rather than gradual assembly. This is the unresolved tension at the heart of modern planetary science. Formation models explain most planets well, but the most isolated ones sit beyond their reach. They force astronomers to confront the limits of existing theories and to accept that some planets owe their existence not to where they are, but to where they once were. When neither core accretion nor disk instability can convincingly explain how a planet ended up on an extreme orbit, astronomers are forced to step outside the boundaries of single-star systems and consider the broader environment in which stars are born. Stars do not form in isolation. They emerge in clusters, crowded regions where dozens, hundreds, or even thousands of young stars coexist within a relatively small volume of space. In these environments, gravity does not act politely. It interferes, perturbs, and occasionally steals. This is where the stellar flyby capture theory enters the discussion, not as a speculative afterthought, but as a serious mechanism capable of producing the strangest planetary orbits ever observed. In dense stellar nurseries, the average distance between stars during their earlier stages can be measured in thousands of astronomical units rather than light years. Protoplanetary disks overlap gravitationally. Stars pass close enough to each other to distort disks, truncate them, or destabilize newly formed planets. These encounters are not rare in young clusters. They are expected. Over the first few million years of a star's life, multiple close encounters may occur. During such encounters, gravitational interactions can fundamentally rearrange planetary systems. A planet orbiting one star can be nudged outward into a highly eccentric orbit. It can be flung into interstellar space, becoming a true rogue, or under very specific conditions, it can be captured by another star entirely. Capture does not require a direct collision or an implausibly precise alignment. It requires energy loss. In a three-body interaction, two stars and a planet, energy can be redistributed in ways that leave the planet gravitationally bound to a new host star. The resulting orbit is typically wide, eccentric, and weakly bound, matching many of the extreme systems observed today. What distinguishes capture origin planets from those formed in situ is not just their distance from the star, but the nature of their orbits. Captured planets often exhibit inclinations that are misaligned with the star's equatorial plane. Some orbit at extreme angles, even retrograde. Others show eccentricities far higher than what disk-based formation models would naturally produce. These features are fingerprints of a violent past. Observational evidence increasingly supports this scenario. Several wide-orbit planets orbit stars whose disks show signs of past disruption. In some systems, debris disks appear warped or truncated, consistent with a past stellar flyby. In others, planets orbit far outside the main disk plane, suggesting they did not form within that disk at all. Stellar capture also offers a compelling explanation for planets found at distances where no reasonable disk could ever have existed. At thousands of astronomical units, a planet is so loosely bound that even a modest gravitational perturbation could detach it. Such distances are more naturally explained by capture than by formation followed by migration. Migration mechanisms, whether driven by disks or planet-planet scattering, struggle to push planets outward to such extremes without ejecting them entirely. The environment of star formation is central to this theory. Most stars, including Sun-like stars, are believed to form in clusters. These clusters dissolve over time, their stars drifting apart and joining the galactic field. By the time a planetary system is billions of years old, the memory of its birth environment is gone. The planets remain, but the crowded neighborhood that shaped them has vanished. This creates a profound observational challenge. Astronomers studying mature systems are seeing the final configuration, not the formative chaos. A planet on a wide orbit may appear inexplicable when viewed in isolation, but perfectly reasonable when placed back into the dense stellar nursery where it likely originated. Captured planets also blur the distinction between bound planets and rogue worlds. A planet that is weakly bound today may not remain so indefinitely. Over long timescales, passing stars, galactic tides, or molecular clouds can strip these planets away, turning them into free-floating objects. This suggests that the population of rogue planets and the population of ultra-wide orbit planets are not separate categories, but points along a continuum. Some planets may have been captured only temporarily. Others may be captured long after their formation, during later encounters as stars move through the galaxy. In regions like stellar streams or remnants of dissolved clusters, encounters remain possible even billions of years after formation. This opens the possibility that planetary capture is not confined to the early stages of stellar evolution. The stellar flyby capture theory also addresses a subtle but important problem in disk instability models. Disk instability tends to produce massive objects quickly, but it does not easily explain why those objects would end up on stable, extremely wide orbits without migrating inward or being ejected. Capture bypasses that issue entirely. The planet forms elsewhere under different conditions and arrives already placed on a distant orbit. Critically, capture does not require that the planet originally formed around a star similar to its current host. A planet could form around a massive star with a large disk, then be captured by a smaller, lower-mass star during a close encounter. This decouples planetary properties from stellar properties in ways that challenge assumptions embedded in formation models. This decoupling may already be visible in observational data. Some wide-orbit planets appear unusually massive relative to their host stars. Others have atmospheric compositions that do not match expectations based on their star's metallicity. These inconsistencies make sense if the planet did not form in the same disk as the star it currently orbits. Numerical simulations support the plausibility of capture. When young clusters are modeled with realistic stellar densities and velocities, capture events occur naturally. While not common, they are frequent enough to account for a significant fraction of wide-orbit planets. The simulations also reproduce the observed properties of these planets: wide separations, eccentric orbits, and weak gravitational binding. The rarity of extreme systems does not argue against capture, it supports it. Capture is not expected to dominate planetary populations. It is expected to produce outliers, and it is precisely these outliers that challenge formation models and force the development of new theories. Importantly, capture does not operate in isolation. It interacts with other mechanisms. A planet may form through disk instability around one star, be scattered outward by interactions within that system, and then be captured by another star during a flyby. These layered histories complicate classification but reflect the true complexity of astrophysical systems. The idea that planets can change stars fundamentally alters how planetary systems are interpreted. It suggests that some planets are immigrants, not natives. Their current orbits tell only the final chapter of a much longer story that spans multiple stars and environments. This perspective reframes the problem of defiant orbits. Instead of asking how a planet formed so far from its star, astronomers ask a different question: did it form there at all? In many cases, the most parsimonious answer may be no. As more wide-orbit planets are discovered and characterized, the role of capture is likely to grow in importance. Upcoming surveys and instruments will be able to measure orbital inclinations, eccentricities, and atmospheric compositions with greater precision. Each of these parameters offers clues to a planet's origin. Planets that defy formation models are not anomalies to be dismissed. They are records of interactions that shaped planetary systems long before they settled into the quiet configurations observed today. Stellar flybys, captures, and ejections are not rare cosmic accidents. They are integral to the history of stars and planets alike. What happens to planets when stars die? When a star begins to die, the change is not sudden or quiet. It is slow, violent, and deeply disruptive to everything orbiting it. Planets that spent billions of years in stable paths find themselves inside a system that no longer obeys the rules it once did. Gravity weakens, mass is lost, orbits stretch, and in many cases planets are destroyed or thrown away into space. What remains after a star's death is not an empty grave, but a distorted planetary system filled with survivors, debris, and objects that should not still exist. The process begins when a star like the Sun exhausts the hydrogen fuel in its core. Nuclear fusion slows, the balance between gravity and outward pressure breaks, and the core contracts. As it contracts, temperatures rise, igniting hydrogen in shells around the core. This causes the outer layers of the star to expand dramatically. The star enters the red giant phase, swelling to hundreds of times its original size. For any planets close to the star, this phase is catastrophic. Orbits that were once safely distant are suddenly inside the star's atmosphere. Mercury and Venus are almost certainly doomed when the Sun reaches this stage. Earth's fate is uncertain but grim. Even if not directly engulfed, intense heat and drag from the star's expanded outer layers would strip atmospheres, melt surfaces, and destabilize orbits. Planetary engulfment is not a gentle absorption. As a planet enters the swollen outer layers of a red giant, it experiences extreme friction. The planet slows down, spirals inward, and deposits energy into the star's envelope. In some cases, this energy can briefly increase the star's brightness or alter its structure. Astronomers have observed red giants with unusual chemical signatures and rotational speeds that suggest they recently consumed planets. Gas giants fare no better. While they are larger, their low density makes them vulnerable. Their atmospheres are stripped rapidly, and their cores may not survive long inside the star's envelope. Some models suggest that a massive gas giant could survive briefly, spiraling inward before being destroyed, while transferring angular momentum to the star. This interaction can spin up the red giant, leaving behind clues long after the planet is gone. Not all planets are swallowed. As the star loses mass through powerful stellar winds, gravity weakens. The star sheds a significant fraction of its mass into space, especially during the later stages of red giant evolution. This mass loss changes the gravitational grip holding planets in place. Orbits expand. Planets that were once tightly bound move outward, sometimes dramatically. For planets farther from the star, this expansion can mean survival, but it comes with instability. As orbits widen, resonances between planets can break. Planet-planet interactions that were once stable can become chaotic. Worlds can be scattered into new orbits, collide with each other, or be ejected entirely from the system. Many rogue planets may owe their freedom to the death of their parent stars. Ejection events are especially likely in systems with multiple massive planets. As the star loses mass, the reduced gravity lowers the energy needed for a planet to escape. A close gravitational interaction between planets can provide the final push. One planet may be thrown outward into interstellar space, while another moves inward or onto a highly eccentric orbit. These events can happen millions of years after the star first begins to die, long after the red giant phase appears complete. After shedding its outer layers, the star leaves behind its core. For Sun-like stars, this core becomes a white dwarf. Roughly the size of Earth, but with half the Sun's mass, a white dwarf is an object of extreme density and gravity. It no longer produces energy through fusion. It cools slowly over billions of years, fading from white-hot to dim red. What remains of the planetary system after this transformation is often shocking. Planets that survived engulfment and ejection now orbit a star that is a fraction of its former mass and size. Orbits that were once measured in astronomical units are now vast compared to the tiny white dwarf. A planet that once orbited at a distance similar to Earth's orbit may now be several astronomical units away. White dwarf systems have become one of the most important tools for studying the fate of planets after stellar death. Astronomers have detected planets orbiting white dwarfs, but more importantly, they have detected something else: pollution. White dwarfs should have clean atmospheres composed almost entirely of hydrogen or helium. Heavy elements like calcium, magnesium, and iron should sink rapidly into the star's interior and disappear from view. Yet many white dwarfs show these heavy elements in their spectra. The only explanation is ongoing accretion of rocky material. This material comes from the remnants of planetary systems. Asteroids, moons, and shattered planets are perturbed inward and torn apart by the white dwarf's intense tidal forces. The debris forms a disk, then rains down onto the star's surface. These polluted white dwarfs act as cosmic autopsies. By analyzing the elements present, astronomers can reconstruct the composition of the destroyed bodies. In some cases, the ratios match those of Earth-like rocks. Iron cores, silicate mantles, even water-rich material have been inferred. This is direct evidence that rocky planets formed, survived for billions of years, and were later destroyed after their star's death. Some planets remain intact and detectable. A few giant planets have been found orbiting white dwarfs at large distances. Their survival suggests they were far enough out to avoid engulfment and chaotic scattering. However, their presence also plays a role in destabilizing the system. A surviving giant planet can gravitationally perturb smaller bodies, sending them inward toward the white dwarf, fueling the observed pollution. In rare cases, planets have been detected extremely close to white dwarfs, on orbits that should not exist based on standard evolution models. These planets could not have survived the red giant phase in their current positions. The leading explanation is migration after stellar death. Gravitational interactions, possibly involving other planets or debris disks, moved these planets inward long after the star became a white dwarf. These close-in planets experience extreme conditions. The white dwarf's gravity produces strong tidal forces. Radiation levels are intense, yet some may retain atmospheres, at least temporarily. The existence of such planets forces a re-evaluation of planetary survival and movement in post-main sequence systems. The death of a star does not erase its planetary system, it reshapes it. Inner regions are cleared through engulfment. Middle regions are destabilized through mass loss and scattering. Outer regions may remain relatively untouched, but slowly evolve under weakened gravity. The final architecture often bears little resemblance to the original system. This process has implications far beyond individual stars. White dwarfs are common. The Milky Way contains billions of them. If planetary systems are equally common, then the galaxy is filled with the remnants of dead systems, populated by surviving planets, drifting debris, and countless objects that were once part of orderly orbits. Some of these remnants may become rogue planets. Others may remain bound, but barely so, vulnerable to external perturbations. Over long timescales, even these systems can dissolve. Passing stars, galactic tides, and molecular clouds can strip away distant planets, adding to the population of isolated worlds. The study of dead stars and their planets provides a glimpse into the long-term future of planetary systems, including our own. It reveals that planetary death is not a single event, but a prolonged sequence of destruction, survival, and rearrangement. Each phase leaves observable traces, from engulfment signatures in red giants to polluted atmospheres in white dwarfs. Astronomers continue to search white dwarf systems for planets, debris disks, and chemical clues. Every detection adds detail to a picture that was once purely theoretical. These systems show that planets do not simply disappear when stars die. They are broken, scattered, transformed, and in some cases left behind to orbit the dense core of a star that no longer shines as it once did. WD 1856 plus 534b, a planet orbiting a dead star. WD 1856 plus 534b is one of those discoveries that immediately made astronomers stop and recheck everything. Not because it was faint or hard to measure, but because it existed at all. A Jupiter-sized planet, intact, orbiting a white dwarf, a dead star, a stellar core that should have destroyed or expelled anything that came too close long before it ever cooled into a white dwarf. The system is located about 80 light-years from Earth, close in cosmic terms. The white dwarf, WD 1856 plus 534, is the remnant of a sun-like star that exhausted its nuclear fuel, expanded into a red giant, shed its outer layers, and collapsed into a dense Earth-sized object with about half the mass of the Sun. That process alone should have erased any nearby planets. Yet WD 1856 plus 534b is there, completing a full orbit every 34 hours. The planet itself is roughly the size of Jupiter. Its mass is constrained to be less than about 14 times Jupiter's mass, placing it clearly below the threshold for brown dwarfs. This matters because it removes one possible explanation. This is not a failed star masquerading as a planet. It is a true giant planet, orbiting something that no longer qualifies as a star in the traditional sense. The discovery came from data collected by the Transiting Exoplanet Survey satellite, TESS. The signal was unmistakable. Every 1.4 days, the white dwarf's light dropped sharply as the planet passed directly in front of it. Because white dwarfs are so small, a Jupiter-sized planet blocks a huge fraction of their light. The transit depth was extreme, close to a total eclipse by exoplanet standards. This made the detection unusually clean and left little room for ambiguity. Follow-up observations using ground-based telescopes confirmed the signal. Spectroscopic measurements ruled out a stellar companion. The object causing the transit was too small and too low mass to be anything other than a planet. The orbit was tight, circular, and stable. Every measurement reinforced the same conclusion. A giant planet was orbiting a white dwarf at a distance of only about 0.02 astronomical units. That distance is the core of the problem. During the red giant phase, the progenitor star would have expanded far beyond this orbit. Any planet originally located there would have been swallowed whole. Drag inside the star's envelope would have caused rapid orbital decay, leading to destruction. There is no scenario in which a Jupiter-sized planet could sit at this distance and survive that phase intact. So WD 1856 plus 534b could not have always been there. This immediately shifted attention from formation to migration. If the planet did not form in its current orbit, it must have moved there after the star's death. That alone is rare. Planetary migration is usually associated with gas disks around young stars, not with stellar corpses billions of years old. The system provides a critical clue. WD 1856 plus 534 is not alone. It is part of a triple system, accompanied by two distant red dwarf stars orbiting each other far from the white dwarf. This wide binary pair introduces long-term gravitational effects that can reshape planetary orbits over time. One leading explanation involves a process known as Kozai-Lidov oscillations. In systems with multiple massive bodies on inclined orbits, gravitational interactions can slowly trade orbital inclination for eccentricity. Over millions or billions of years, a planet's orbit can become extremely elongated. At its closest approach, the planet passes very near the central object. Tidal forces then dissipate energy, shrinking and circularizing the orbit. In this scenario, WD 1856 plus 534b originally orbited much farther out, well beyond the reach of the red giant's envelope. After the star became a white dwarf, gravitational perturbations from the distant stellar companions gradually altered the planet's orbit. Each close pass near the white dwarf drained orbital energy, until the planet settled into the tight orbit observed today. This process is slow, chaotic, and highly dependent on system architecture. It explains why such planets are rare. The conditions must be just right. The planet must survive the red giant phase at a safe distance. The system must include additional massive bodies capable of driving orbital changes. The planet must avoid being ejected or torn apart during the process. Even with this explanation, the system remains unsettling. The planet orbits so close that its equilibrium temperature, despite the white dwarf's low luminosity, is estimated to be several hundred Kelvin. The planet receives intense tidal forces. Its atmosphere, if it has one, is constantly stressed. Yet it remains gravitationally bound and dynamically stable. WD 1856 plus 534b also challenged assumptions about white dwarf planetary systems. Before this discovery, evidence for planets around white dwarfs came mostly from indirect signs: polluted atmospheres, debris disks, and disintegrating asteroids. A fully intact gas giant planet in a close orbit had not been confirmed. The discovery triggered massive media coverage in 2020. Headlines emphasized the shock value: a planet orbiting a dead star, a world that survived stellar death, a system that should not exist. The attention was not exaggerated. This was a direct observation of a planetary survivor in a configuration that theoretical models had long considered improbable. For astronomers, the system became a test case. It forced revisions to models of post-main sequence planetary evolution. It showed that planets can remain dynamically active long after their stars stop fusing hydrogen. It demonstrated that migration does not end when the protoplanetary disk disappears. Gravity continues to reshape systems on timescales of billions of years. The implications extend to the broader population of rogue and isolated planets. Systems like WD 1856 plus 534 suggest that many planets may be displaced during stellar death, either thrown outward into wide orbits or ejected entirely. Some of the free-floating planets detected in the galaxy may be the final products of these late-stage instabilities. The system also reframed how astronomers think about habitability timelines, not in terms of life, but survival. Planets are not static companions to stars. They are subject to extreme changes long after formation. A planet that begins its existence in a stable orbit can end up migrating inward toward a stellar remnant billions of years later. WD 1856 plus 534b stands as direct evidence that planetary systems do not freeze after stellar death. They remain active, reshaped by gravity, companions, and time. The planet's existence is not a loophole in physics, but a consequence of it operating over immense timescales under uncommon conditions. As more white dwarfs are monitored with transit surveys and infrared instruments, systems like this are expected to emerge again, though rarely. Each one adds weight to the idea that the galaxy is filled with planetary remnants, survivors, and objects in transitional states between bound worlds and true rogues. WD 1856 plus 534b is not remarkable because it is large or hot or bright. It is remarkable because it is there at all, circling the dense core of a star that once expanded enough to destroy nearly everything close to it, yet somehow left this planet behind, intact, displaced, and still orbiting. Planets around pulsars, the ultimate isolation. The discovery of planets around pulsars is one of the most shocking chapters in exoplanet science because it turns everything we think we know about planetary survival upside down. Pulsars are the remnants of massive stars that exploded in supernova, leaving behind incredibly dense neutron stars spinning hundreds of times per second. The radiation environment around these objects is extreme. Intense X-rays, gamma rays, and high-energy particles stream outward constantly, sterilizing anything in their vicinity. To find planets orbiting such a star was once thought impossible, yet here they are, orbiting in the most hostile conditions imaginable. The story begins in 1992, when Alexander Voltsan and Dale Frail published their discovery of planets orbiting the pulsar PSRB 1257 plus 12. These were the first confirmed exoplanets ever detected, predating the detection of planets around Sun-like stars by several years. Their existence was immediately puzzling. How could planets survive the violent death of a massive star, an event that typically ejects most of a star's mass and generates shockwaves capable of destroying nearby worlds? These pulsar planets are not in standard stable environments. The pulsar's intense magnetic field and rapid rotation generate radiation far beyond what a normal star emits. Any planetary atmosphere would be stripped quickly. Surface temperatures are irrelevant because the planet is irradiated by high-energy particles. In many ways, these planets exist in a state that is almost purely gravitational. They orbit a star that can't provide warmth or light in any conventional sense. Survival in this context is entirely a matter of remaining gravitationally bound, shielded from catastrophic collisions, and not expelled by interactions with residual debris from the supernova. Astronomers now consider pulsar planets cosmic survivors in the truest sense. They may have formed after the supernova from fallback material rather than surviving the star's death. Alternatively, they could have been captured from another system. Either way, their presence tells us that planetary formation and survival can occur under conditions far more extreme than previously imagined. These planets orbit in isolation, exposed to the galaxy's harshest radiation environments, yet they persist as testaments to resilience in the most extreme corners of the universe. Planets in intergalactic space. The idea of planets existing beyond the boundaries of any galaxy might seem like science fiction, yet serious astrophysics suggests these worlds could exist in intergalactic space. The mechanisms that could place a planet between galaxies are violent and rare, but they are not impossible. Galaxy collisions, tidal interactions, and cluster ejections all create conditions in which planets can be stripped from their home systems and cast adrift in the vast emptiness between galaxies. During galaxy collisions, gravitational forces stretch and distort the participating galaxies. Stars are tugged from their original orbits. In extreme cases, entire clusters of stars can be flung into intergalactic space. Planets that remain bound to these stars are carried along, but some planets experience additional forces that strip them entirely from their hosts. These worlds are left to drift alone, isolated not only from their star, but from any nearby stellar population. Tidal stripping is another pathway. As galaxies interact, differential gravity, where one part of a galaxy experiences a stronger gravitational pull than another, can tear stars and their planetary systems away from the galactic disk. Planets orbiting at the outskirts of systems are particularly vulnerable. Even planets initially bound to stars may find themselves ejected during these violent encounters, ending up as free-floating intergalactic planets. Cluster ejections provide yet another channel. In dense clusters, multi-body gravitational interactions are common. A star may pass close enough to another system to perturb or eject a planet. If this occurs near the edge of a galaxy, the ejected planet can escape not only its host star, but the galaxy entirely. Over billions of years, these intergalactic wanderers could drift silently, far from any stellar neighborhood. Astronomers have not yet observed intergalactic planets directly, but indirect evidence and simulations suggest they exist. Theoretical models indicate that for every galaxy there could be billions of planets roaming the space between galaxies. These worlds are isolated on the largest scales possible, billions of light-years from the nearest star, orbiting nothing, truly alone in the cosmic void. They challenge conventional notions of planetary systems, demonstrating that planets are not always tied to stars, galaxies, or even the regions we consider home in the universe. Intergalactic planets are the ultimate testament to cosmic isolation. They exist in silence, without a star to illuminate them, without a cluster to provide gravitational context, drifting across voids measured in millions of light-years. The existence of such planets, even as a theoretical prediction, expands the boundaries of where planets can exist and how we define them. In this sense, the universe may be far stranger than any system of stars and planets we have ever observed, populated by countless solitary worlds wandering in darkness, beyond the reach of any galaxy. Discovering isolated planets requires methods completely different from those used to detect planets close to bright stars. Traditional techniques like radial velocity or transit photometry rely on the planet exerting a detectable effect on its host star. When there is no host star, these methods are useless. To find rogue or ultra-isolated planets, astronomers turn to techniques sensitive to the planet itself or to the planet's gravitational influence on background light. Gravitational microlensing has been the cornerstone of these discoveries. The principle is elegant and subtle. A massive object passing between Earth and a distant star can bend the star's light through gravity, creating a temporary brightening. If a planet is the intervening mass, the light curve exhibits a brief, distinct spike, sometimes lasting hours or even minutes. Unlike other methods, microlensing does not require light from the planet or its star. It can detect objects entirely dark, invisible in conventional telescopes, making it ideal for finding planets that wander alone through space. Microlensing surveys in the 1990s and 2000s predicted populations of Earth to Jupiter-sized rogue planets, and by the 2010s, detections began to confirm these predictions. Each event, though fleeting, provides a direct measurement of the planet's mass and distance, revealing worlds that would otherwise remain hidden forever. Direct infrared imaging complements microlensing by allowing astronomers to detect young, massive planets that retain enough internal heat to glow faintly in infrared. Unlike visible light, which is dominated by the glare of nearby stars, infrared light can reveal planets that emit their own warmth. Instruments on ground-based observatories like the Very Large Telescope and Keck have captured images of ultra-wide orbit planets, revealing gas giants orbiting hundreds of astronomical units from their stars. These observations not only confirm existence, but also allow spectral analysis, showing atmospheric composition, clouds, and temperature. Direct imaging is limited, however, to the most massive and warmest planets, meaning countless smaller, colder, isolated worlds remain invisible. The James Webb Space Telescope has dramatically expanded these capabilities. JWST's infrared sensitivity and high-resolution imaging can capture planets that were previously beyond reach. Unlike ground-based telescopes, JWST avoids atmospheric interference, allowing far deeper and cleaner observations. It has imaged objects like HIP 65426b with unprecedented clarity, producing spectra that reveal the chemical fingerprints of distant, isolated gas giants. JWST also allows astronomers to probe planets that are not orbiting stars closely, providing a new window into the population of wide-orbit and potentially rogue planets. Looking forward, the Roman Space Telescope promises to revolutionize the field further. Designed with a wide-field survey camera and high-precision microlensing capabilities, Roman will detect thousands of planets, including those that are unbound or extremely far from their stars. Its surveys will probe the outer edges of planetary populations in the Milky Way, providing statistical samples large enough to estimate total numbers, mass distributions, and orbital properties with unprecedented accuracy. Despite these advances, most isolated planets will never be seen directly. Even JWST cannot image a cold Earth-mass planet drifting alone in the galactic field. The vast majority of rogue worlds are too small, too faint, and too distant. Our knowledge relies on indirect detection methods and statistical inference. Each detection is a rare glimpse into a hidden population that likely dwarfs the number of stars in the galaxy. Observational limits mean we are only scratching the surface. What we see is the tip of an immense cosmic iceberg, hinting at billions of unseen worlds adrift in darkness. Estimates of the total number of isolated planets in the Milky Way are staggering. Microlensing surveys suggest that there may be as many or even more rogue planets as there are stars. Some analyses imply that for every star in our galaxy, there could be one or more planets wandering alone, unbound to any host. This fundamentally alters our understanding of planetary populations. Planets are not rare companions. They may be just as numerous as stars themselves, only far more hidden. These numbers reshaped planetary science because they revealed that the traditional focus on stable, star-bound systems was only part of the picture. The Milky Way is not just a collection of neatly organized planetary systems. It is a chaotic mix of bound and unbound worlds. The presence of billions of isolated planets implies that formation, scattering, and ejection are not exceptional events, but normal outcomes of planetary system evolution. The galaxy is far more dynamic than previously imagined, with planetary chaos sculpting populations on every scale. Isolation is more common than stability for a simple reason. Planetary systems are inherently chaotic. In the early stages, multiple planets form in crowded disks. Gravitational interactions among them, combined with the influence of the star and the dissipating gas disk, lead to collisions, mergers, and ejections. Close encounters can send planets outward, some eventually leaving their systems entirely. Even if a planet survives these early storms, the death of the host star or later interactions with passing stars can destabilize its orbit. Over billions of years, a significant fraction of planets will drift away from the stability of their natal systems. This statistical inevitability means that isolated planets are not anomalies. They are expected outcomes of the same physical processes that shape all planetary systems. Observing them is difficult, but theory predicts their numbers must be immense. Each detection through microlensing, direct imaging, or future JWST and Roman surveys confirms what simulations have long suggested. Isolation is the default, and stability is the exception. The universe is teeming with planets, but the majority exist in silence, unlit by a nearby star, adrift across the galaxy, invisible yet pervasive, a hidden population that challenges every assumption about where and how planets survive.